You have the card, the card.
I'm the Associate Director of Midshipman Research, and today I'm going to be your moderator for these Trident scholars giving their presentations, talking about the research that they've done all year. This goes throughout the whole day, so if you have to leave and come back, please do so. But before we get started, I'm going to introduce Provost Samara Firebaugh. She's going to say a few words.
Good morning, everybody.
Good morning, ma'am.
So I know tomorrow is the banquet fancy thing. The heart of the Trident conference is today, as we hear about the fantastic work that you've done over the course of the year. I want to make sure I tell you how proud I am of you. This program, the Trident Scholar Program for the parents and for the parents online, it takes true dedication. I know for many, many hours of the lab, right? I hope that depth of engagement, I hope that it stretched you. I hope you found satisfaction in it. I hope you take those critical thinking skills and bring them into your future career. So thank you so much for your commitment to this program. I look forward to seeing your talks. Now, I promised to ask a question of each of you when I see you today. Now, some of you I might miss. I have a few meetings I have to step out. So I promise if I miss you at the presentation, I will get you at the poster session. So no worries. You'll definitely get a question from me so you can show off all your hard work. With that, no further ado, we should get started. Thank you.
We appreciate the support from senior leadership, Provost's office for this program. We're going to start with our first Trident presentation. It's going to be Robert Cohen. He's from the 9th Company from Strongsville, Ohio. His service assignment is submarine warfare, and he's a 4-time letter winner for the Navy Men's Lightweight Crew Team.
Good morning, everyone. My project is modeling operational disruptions due to flooding using Bayesian networks. Oh, shoot. I just clicked the wrong button already. I don't know what just happened there. Okay, we're good. Anyways, so the motivation for this project came from my personal experience with flooding at the Naval Academy. As many people here probably know, we've seen a lot more flood events recently at the Naval Academy. A lot of these events have caused a lot more operational disruptions than we've seen in the past. Because of this, I was really interested in looking at what potential ways we could figure out how to harden our infrastructure and in the end make sure we were still able to operate the Naval Academy. Through this research that I was doing, I came across Professor David Alderson of the Center for Infrastructure Defense at Naval Postgraduate School. During this conversation, we talked a lot about the mathematical models that were involved with modeling operational disruptions and infrastructure disruptions, as well as the problems that these math models were currently facing. During this conversation, we established 4 of the main issues with climate disruptions. The first one is that climate disruptions are not intelligent attackers. This means that they don't necessarily impact the most important piece of infrastructure that is going to impact the most operations at an institution. Because of this, we have to look at each piece of infrastructure for an institution separately, and on top of that, each operation separately, and the effects of infrastructure on those operations. Another thing is we know that flood events are becoming more frequent. Because these flood events are becoming more frequent, again, our operations are becoming more impacted. How can we model this in such a way where we can start to answer questions about fortifying our institutions in order to make them less affected by these events? Another thing is we need to quantify operational risk. This is a little difficult because we have so many different missions and so many different pieces of infrastructure that we are dealing with under these flood conditions. Fourth and final thing, probably the most obvious, is that naval infrastructure is near water. This is important because it needs water to do its job in order to, have ships and all of those various activities that the Navy does. To get more into the background of why the Naval Academy is probably an important case study for this type of modeling is a forecast from this past February. It's just one day in February. There's minor coastal flooding. Great, just one day. Let's look at the next day. All of a sudden, we have 2 flood events for the next day, and one of which is possibly a moderate coastal flooding event, so even higher. Let's look at the rest of the week. That's a lot of flood events. More specifically, we had 3 moderate flood events and 9 minor flood events projected from the 5th through the 9th of February 2024. Again, this is just a snapshot in time, so we really want to understand the overall trend of what is happening when it comes to flood frequency. This is where we used NOAA tidal and currents data from Annapolis, Maryland station in order to better understand what sea level is looking like over time. From 1965 to 2023, we were able to get hourly sea level data, and with this hourly sea level data, understand the amount of flood hours on average per year. Very noticeably, after about the year 2000, there's a drastic increase in the amount of minor flood events with a slight increase in moderate flood events. For me, as a mathematician, I'm seeing this as a distribution of sorts is shifting. But what is that shift and how can we quantify it in order to better understand how it's affecting our institutions? To do this, we looked at one of those 5-year periods that were used for the previous graph, and we created a histogram out of that hourly data. This is from the year 2000 to 2004. Very notably, it is bell curve shaped, which means that we can start to look at 2 statistics specifically, one of which is average and the other is standard deviation. The average value, of course, is just the basically line down the middle where you would draw that. The standard deviation is going to be the average value or the average difference in values from that average value of the distribution. We wanted to look at these 2 statistics specifically and how they changed over time. More specifically, we looked at average sea level from 1965 to 2023, and there was a positive trend. This agrees with most of the current literature out there that says that the sea level is rising, but another thing we noticed is that it's fairly linear. So we decided to draw a line. Not just any line, though. We used linear regression to draw this line, and we noticed that through this mathematical concept, we're able to obtain an R-squared value of 0.95, which means that 95% of the variability in the average sea level is described by the red line here. This is a pretty good fit that's going to help us for future analysis and projection later on when we get to modeling. Now that we've talked a lot about the sea level and how that's changing, what are the actual impacts of the sea level? Well, we know that Hospital Point parking is getting affected. There's flooding over there. We've had to wet and dry flood-proof our academic buildings in order to prevent our basement floors from getting flooded. Another thing is we have nuisance flooding on major roads that are important for regular transportation throughout the academy. This allows basically no passability through that road. Now that we've talked about flooding and operations, we can then start to talk about the risk associated with these events. More specifically, the Navy has a common risk assessment matrix that they use when you are determining if an evolution is very safe or not safe at all. The only issue with this matrix is that it's looking at one hazard and the probability of that one hazard affecting one event. In our case, we are looking at one hazard, flooding, but it's affecting many pieces of infrastructure which affect a few operations. Because of this, it makes it very hard to apply a regular matrix like this in order to understand the actual risk assessment associated with our institutions. In order to, I did it again. There you go, sorry. In order to understand how we are going to model this risk, we need to understand the probabilities associated with risk. So we're going to go through a little bit of probability theory. We know that probabilities are measured between 0 and 1, and this can be converted into percentages. 0% is the event cannot occur, and 100% is the event has to occur. Any value between 0 and 100 means there's a chance of that event occurring. So we can use probability to answer questions like, how likely is sea level greater than 1.8 feet? Or how likely is a road to flood? These can be described using probability statements, like the probability that sea level is greater than 1.8 feet is around 20%. We were able to get the 20% from our analysis we did with our sea level distributions. Now we want to look at the road. So the probability that the road floods is dependent upon our sea level height. Because of that, we need to know how high that road is, and we need to know how often that sea level height happens. In this case, we decided that the road was 2 feet high, which means that the probability that the road floods is about 13%, which is, of course, less than 20% because the road is higher than 1.8 feet. Like I described, sea level impacts flooding. This is the idea of a conditional event. We can describe this through the conditional probability statement. The probability that the road floods, given that the sea level is 1.8 feet, is 65%. This is important because it gives us a little more information if we already know something about the current state of sea level. More specifically, if we predict that sea level is going to be 1.8 feet more commonly in the future. Now that we've talked about probability theory, we can then move to the modeling strategy we are going to use for our project, which is Bayesian networks. For example, we're going to take a random variable called security exercise, which is distributed with yes or no, depending on how often a security exercise happens. More specifically, we decided that a security exercise, let's say, happens once a month, which means 12 over 365, or about 3% of the time, it is yes. The other 97% of the time, it's no. This is great, but it doesn't really tell us much about how security exercises are going to affect other things at an institution. To do this, we're able to create another random variable called gate 8. And we know the state of gate 8 is either going to be open or closed. We know that security exercises is the parent of gate 8 because security exercises can influence if gate 8, its child, is open or closed. Because of this, we end up with two probability distributions. One, if the parent security exercise is not happening, which is the top row of this table over here, and the other if security exercises are happening, which is the bottom row of the table. This is going to be important because this is the establishment of how we are going to determine how our models right here are going to work. More specifically, after some research and fooling around with a bunch of different types of models, we ended up with two ideas based on the granularity of analysis needed and the data you have available. The focused model focuses on the operational utility of our road networks at the Academy. We decided to use road networks because of the publicly available data, as well as the importance of roads for most operations at the Academy, so it still had a significant effect for decision makers to figure out how they should fortify our roads in order to create a more resilient institution. Another model we talked about was the holistic model, which is holistically looking at the Naval Academy and the missions of the institution. Because of this, we are looking at many different pieces of infrastructure and the mission impacts of those infrastructure. Again, because we are looking at more pieces of infrastructure, this model becomes a little more complex. First, let's talk about the road model. Based on the publicly available literature, we were able to determine that there were 5 roads that were impacted by flooding at the Academy. And each of these 5 roads, based off of discussions with subject matter experts, determined that there were 3 operations that roads were mainly responsible for: emergency services, flow-through system, the ability to get from point A to point B, and parking. As you can see, each of these roads affect each of these operations. However, they don't all affect the operations uniformly. Road A might have access to more parking than Road B. Therefore, it would have a greater impact on the parking variable than Road B. Emergency services might be right next to Road B, whereas Road E might be a side road that emergency services don't really need access to. That's how we were able to kind of weight these relationships between these variables. In order to understand how the probabilities kind of propagate and the information propagates through the system, we need to establish a distribution for our sea level variable. More specifically, we took the 5 most recent years of data and we used a fitting algorithm in order to find that the t distribution was a good fit for this model. And you'll see later why this is important for future model projection. So when we put that t distribution for sea level in, and we know the heights of each of the roads, we're able to understand the impacts for each of our operations that roads impact. However, this isn't that significant because it doesn't tell us much about what's going to happen in the future. So in order to do that, we decided to take our average sea level regression that we did earlier and project what the sea level distribution will look like in the future. This is over the next 80 years. Again, you can see that the true value of of all of the roads is increasing as time goes on because that distribution is shifting to the right. Also, again, emergency services, flow-through system, parking are all becoming way more highly impacted than they were in current times. This confirms a lot of what current literature is saying when it comes to the climate impact that is projected into the future as well. Now we can move on to the holistic model. The holistic model, like I said, is focusing on the entire mission of the institution. So those are the bottom 3 variables that we are trying to really understand how they are impacted by sea level. The infrastructure and personnel variable associated with this distribution were a result of the Military Installation Resilience Plan for USNA that came out about a year ago. They focused on academic buildings, roadways, utilities, access gates, and athletic facilities. We also added the support staff variable because it is also another meaningful variable that should be tracked when you are dealing with risk associated with these missions. In order to fit these parameters for initial inputs, we decided to look at data for the maximum impact of sea level for each day. So because we are changing the type of sea level data we are looking at, our distribution shifts a bit. Instead of using a t distribution, we're using a Johnson SU distribution. On top of that, we needed a way to be able to determine the initial input parameters for all of our other variables in our model. To do this, we consulted experts as well as using our own general knowledge of the Academy in order to come up with some initial inputs that seem to make the most sense for the child variables of sea level. However, the main goal of this model is not necessarily just to create it, but the fact that it can be updated over time, given that you have actual data to deal with. In our case, we weren't able to start off with actual data because a lot of it is controlled unclassified information, but we can still create a framework that will allow people to update this model in the future. More specifically, we came up with a survey that each row of this table here is a input from that survey. More specifically, again, it is the maximum impact of each variable for that day. Now that we have this data, we need a way to update our prior parameters in order to gain a better sense of what truly is happening within our model and the institution. To do this, we came up with an updating rule based off of, again, Bayesian probability theory. To do this, it is just, we are just weighting the prior input that we had and then the amount of counts of data. And through this, we're able to then update our distribution. So again, let's go back to our initial input. This is what it looks like. You guys have seen it already. But let's say that we know that sea level is going to rise in the future, which means that our child variables are going to become more impacted. So we took 365 days of simulated impact data for a higher sea level, and all of a sudden, we end up with this distribution. As you notice, things like roadways have higher medium impact. Things like support staff have higher medium impact, professional mission, so on and so forth. As well as you notice, the sea level distribution is, of course, not as smooth because we are using real data at this point as well. In conclusion, Bayesian networks are effective modeling tools when you're dealing with interdependent infrastructure and operations of an institution. But you have to have data surrounding that operational impact of flooding in order for this model to be extremely effective. However, we did explore a way through Bayesian updating to update these models given new data, which is great. On top of that, this model also supports something called what-if analysis for decision makers. This is where a decision maker could ask a question like, what if sea level is rising faster than we planned? Or what if our roads are 10 times stronger or 10 times less likely to be impacted than we thought because we put in this mitigation measure? This allows them to do some hypothetical planning before actually putting it into practice at an institution. Another thing that's very unique about our model is that it was all done through Python and open source, and I coded all of it on my personal MacBook, which means that you don't need super fast computing powers in order to run these pretty powerful models. As statistician George Box says, all models are wrong, some models are useful. We're hoping ours falls in the useful category. Any questions?
Yeah.
I have a question for you. So this is great work. You did such a great job explaining the math behind it and what you're seeing. What recommendation would you have for a Naval Academy administrator on what they should do in the face of what you're seeing?
So unfortunately, we were not able to get a lot of the data that would have allowed us to make comments like that. But the hope is that if a decision maker who has access to that data can then just plug it into the model and see the results of that data being plugged in, that they're able to then see the decisions that they need to make. So unfortunately, don't necessarily have an answer to that, but yeah.
So I noticed your first slide, you had the frequency of flooding events, and that was decidedly non-linear, right? I mean, it's basically gone up significantly since whatever, 1995.
Yes.
But sea level rise is a linear function. Do you have reason to believe? So I assume you just extrapolated that.
So this is average sea level. Yes, we extrapolated that for the future.
Do you have reason to believe that that's going to remain linear? That seems like conservative.
Yes, and you could say that again. Like there are things you can witness or recognize about the points in the graph here, specifically like the points up here, are, of course, a little higher than the points down there. Therefore, this is over from 1965 to 2023 when we actually used a linear regression for, I think, again, from I think I did it from 2000 to 2023 in order to get the values associated with the changing sea level here. It was also linear as well. And it got a higher R-squared value of 0.98 as well, which is pretty impressive. So maybe that is a good point, and that's something that we talked about throughout our entire project was at what point does the data shift from necessarily being linear to nonlinear, or at what point should you discount old data because it doesn't match the current data, which is a growing area of time series analysis when it comes to mathematics.
Thank you. Oh, could you go back to the frequency of the flooding slide?
Yeah.
Did something happen in like 2000 that caused such a steep increase?
Yeah. So if I'm not mistaken, when was the hurricane? Is that? That was 2003. My bad. So if we are looking at around like this area right here, which is probably 2003, a lot of those values are probably again impacted by the fact that there was a major storm event that did happen. But then again, like the trend doesn't stop there, which we don't necessarily know what worldwide wise happened to impact that, but I mean the data does show that there was some sort of impact. Yes?
You showed us the graph a second ago about the trend of the average. Did you look at what's happening to the standard deviation or did you keep that constant in your?
Oh, yes. So we also looked at standard deviation as well. The only thing is it was extremely insignificant. We got a very tiny value. The R-squared value, I think, was like 0.2. And it really didn't fit a linear regression when we were looking at it. And again, like I said, it didn't really change over time. It was kind of sinusoidal in pattern. And because of that, we kept standard deviation constant throughout the rest of our modeling. Thank you. Great question. Yes?
Thank you very much for this very interesting presentation, especially in view of the flooding that we've had in the last couple weeks. But my question is, in order to make sure I understand this, you talked about 1.8 feet and 2 feet above. And my question is that 1.8 feet above the average sea level, which is itself rising, in order to be a flood stage? That's what I'm trying to understand.
Yes.
So 1.8 feet indicate 1.8 feet above average sea level.
So I was being very generic here when I was giving these questions, but there are these things called tidal datums that are used. So if you notice a lot of what I wrote here, so hourly water level, mean lower low water. So there are these datums where these things are referenced from, and that's how you get sea level height that's how you get that sea level height that I kind of was talking about. Again, in this case, it was very generic. I didn't really give any datum for it, but it was just supposed to show that you can measure probability, or you can measure the probability that sea level is a certain height, given how high
I'm just trying
that
to
is.
understand what the 1.8 means. It's 1.8 above
So
the average that is, current at a particular time and would constitute, a sea level rise, a local and temporary sea level rise due to rain or tidal, whatever. Is that?
It's to like a relative. So a datum is like a reference point. So it's to like a relative, like how elevation is measured, right? Where you have altitude from like a certain datum. Sea level is measured in much the same way. So that's 1.8 feet from whatever that datum is, and it doesn't necessarily determine if there's flooding or not. However, as I show here, if mean lower low water value in feet is greater than 2.6, then we know minor flooding is occurring. If so on and so forth for moderate and 5-year storm. So that's kind of how they relate to each other. There's a bunch of different datums or tidal datums that are used. Tried to avoid getting into that because it can get a little confusing for me too. But yeah, thank you. Great question. Yes?
Hi, fantastic presentation. I wonder
So again, with support staff, we had it have the same sort of distribution as the other infrastructure and operational variables in our model. The reason we wanted to include support staff was the idea that you might have an academic building, but you might not necessarily have the roadways or the utilities or even the access gates to get people in that academic building to perform the academic mission. So this is sort of another variable to assess not just infrastructure, but the personnel that's associated with achieving certain missions at an institution.
Yeah, Robbie, great presentation. I was just wondering if you looked at other military installations in a similar area, like at the Coast Guard base in New Jersey, if they have similar issues or their ways of combating this.
So there are basically every military installation or coastal military installation and even non-coastal military installation has some sort of climate resilience plan. Again, we have the Climate Action of 2030 report from the Department of the Navy. They're really pushing all this stuff. I didn't necessarily look into other institutions. Personally, from another project I did in another class, Naval Air Station Key West is another place that's undergoing a lot of flooding issues. And so they're looking into ways of increasing infrastructure resilience. And again, there's other researchers working on it, like the Center for Infrastructure Defense at Naval Postgraduate School.
So going off of that question, if you wanted to apply this model and methodology to another installation, would that just be a matter of like changing the input code spreadsheet, or would like you have to change the fundamental model itself?
For the model itself, you would have to, of course, change the. Let's go to the holistic model, right? You could add more variables in terms of the infrastructure, which is great because it's pretty modular in that way with Bayesian networks. And of course, you would have to change the missions based off of what it was. The only thing that would be difficult would be if you wanted to try to start having different types of distributions for each of these variables. That wasn't necessarily built into the model, but all variable types, as long as they're kept the same for the child variables, are relatively easy for you to apply to other institutions. Yes?
I'm curious if you, when you were playing around with the data, got to a point where the Naval Academy would have to move.
I had many discussions about that. I personally wouldn't be the one to make that decision, so it'd be a little difficult. But yes, there are like projections out there and ideas about how we are going to deal with where the Naval Academy is going to be in the next 100 years, if there's even a way to go about fortifying it to the point where it will be resilient enough to last till 2100. Yes?
Thank you for your presentation. I have two questions. The first one is, we already know that we are moving more, like based on all projections, NOAA and DOD is moving more into an intermediate high projection for sea level rise, which is definitely not linear. So how easy will it be to change from linear to nonlinear? So coming back to that question that was asked earlier, your model. And then the second question is also about nonlinearity, because when you talk about supported stuff, we are not in a cycle. So how did you account for things that are happening outside the academy? Like people even getting into the yard, not even as they enter, but even being able to come.
Yeah, so to address the first question, if you are looking at as long as this distribution here stays relatively the same in terms of shape, the only thing that, again, would be changing would be, and the standard deviation stays the same, of course. The only thing that would be changing, again, would be the mean, and the mean would just fit a more, it just wouldn't fit a linear, whatchamacallit, a linear regression. Sorry. And then to answer your second question, we thought of including other roads, like roads outside the academy, like Dock Street and stuff like that, that might affect someone's ability to get to gate 1 or get on the yard. The only issue with that is all of a sudden, then it's like, at what point do you stop looking at, roads that people might drive on? Because, people live in Davisonville, people live in Bowie, stuff like that. So at what point do you stop looking at roads? Because of that, and because this is a test case framework, we wanted to keep it relatively simple while still being significant and giving some sort of insight for decision makers, if that makes sense.
Is something that you add to your model?
Yes, it could.
Probability of people not even showing up.
Sorry?
Like probabilities of people not even showing up because they cannot get.
Yes, and that could be something that you can, again, add to the model. Again, that's one of the great things about Bayesian networks is their modularity, the ability to add more things as you see them. However, at the same time, you also want to keep it as simple as possible, so then you don't necessarily overfit or end up with a model that becomes too hard to understand where the significance is.
Let's thank our speaker one last time.
Do not hit that button.
I'm not even gonna.
Who is from the second company. He's from Situate, Massachusetts. His service assignment is Navy pilot, and he's an astrophysics major.
Hello, everybody. So I'm Jamie Margson, and my Trident project was on the structure of the X-ray continuum emission region in the gravitationally lensed quasar SDSS 1339. So a quick little shout out before I begin to my collaborators at the University of Oklahoma, Dr. Sinyu Dai and Gilberto Garcia, and our European collaborators, Luis Goykache and Vyacheslav Shalyapin. Vyacheslav is Ukrainian, and so he's currently indisposed. He's not in Ukraine right now, so this is the best picture I could find of him. So why study quasars? Why is this so important? Well, quasars are the most powerful and luminous sources of light in the universe, and they're also producing the vast majority of X-rays in the universe. However, we have a very poor understanding of how they are creating these X-rays. So that's a big question in the astronomical community. It's been a debate for decades now. So this is a question we hope to answer in this project. So a little overview of what I'll be discussing today. First, a physical understanding of what is a quasar, and more specifically, what is a gravitationally lensed quasar. And I'll get into our system specifically, SDSS 1339, and then break down my work, broken down into 3 phases, and then finally, discussion on our results. So what is a quasar? Quasar is this object that you see in the center of many distant galaxies, and this is the galaxy in blue, it's the blue haze. And these objects are outshining their own host galaxies by hundreds or even thousands of times. So that's on the order of tens to hundreds of billions of stars that are being outshined by an object in the center of the galaxy. And these quasars are also radiating across the entire electromagnetic spectrum. So this is a plot of luminosity as a function of wavelength, or as a function of frequency on the bottom, or wavelength on the top, however you'd like to think about it. And while galaxies made up of stars will peak really only in the visible wavelengths, this indicated in the red, the quasars will be radiating across the entire electromagnetic spectrum, so very uniformly. But these objects are so far away and they're so small that we can't really resolve them with any telescopes. So they're diffraction limited by our telescopes. They just kind of look like points of light. So they're about the size of the solar system. That's the size that we know that they can be at a max. However, because they're billions of light years away, we just can't resolve them. They just look like points. So what do we think they are? Well, we think that the consensus is that they are accretion of matter onto supermassive black holes that we see in every galaxy. So here's a black hole. It's the black dot in the center. And there's an accretion of matter surrounding it. And as the matter falls into the black hole, through friction and other forces, it's radiating out a lot of light. And you can see here there's also relativistic jets of excited matter that shoot out of the magnetic poles of the black hole. However, we don't exactly know, there's no consensus onto how the X-rays are being created in this object. But remember, they are creating the vast majority of these X-rays that we see in the universe. So there's two leading models. There's been this debate for decades now. The first, the older, more conventional model, is the disk corona model that says that X-rays are being created in a hot corona of gas that surrounds the accretion disk. Now, the accretion disk can extend out to hundreds of gravitational radii away from the black hole. Gravitational radii are the scale radius of a black hole, what you would think of as the radius of the black hole. And so this model says that X-rays are being emitted as far out as these hundreds of gravitational radii from the center of this object. Now, the newer model, the lamppost model, or the aborted jet model, says that X-rays are being created very close to the black hole in the relativistic jets. And this says that the X-ray source size is about 3 gravitational radii from the center of the black hole. So very different models. And the best way to figure out which model is correct, a good answer to this debate, is figuring out the size of this X-ray emission region. So that's what my Trident project was all about. Now, these objects, remember, are very tiny. So we have to employ something called gravitational lensing to really understand how to figure out a size of this X-ray emission region. Now, gravitational lensing says that light likes to travel straight through space. However, if you put a massive object, what we call a lens, in the path of this light, the light will now be deflected and warped around this lens because the lens will warp space-time. And so the observer will see a source of light, not necessarily where the source is, but a little deflected off of the lens. And so the observer will actually see multiple different sources or mirages of this light source around the massive object in the foreground. And these lenses can also act as magnifying lenses. That's why we call them lenses. So they can actually brighten the source in our mirages. So we can see the source light a little bit brighter or a little bit dimmer than the actual source itself. And so this is an example of a different quasar where it is behind a foreground galaxy. So here's a lensing galaxy in the foreground, and behind this is the actual quasar. However, we don't see the quasar itself. We see mirages of the quasar around this galaxy. And it's also important to note that, as you can see here, the paths that the light takes from the source to the observer are different lengths. And so quasars are inherently variable, so they brighten and dim over time. But this, as the source of light will brighten and dim, you'll see that brightening and dimming effect in different images at different times. So you might see it in image A as it gets brighter and then gets dimmer, and then you'll see it in image B a little bit later. It gets brighter and it gets dimmer. And this is known as the time delay of the system. So that's important to note. It's also important to note that these images will sometimes pass through the disk of the galaxy. So here is the foreground galaxy. It's this oval right here. And the images of a background quasar will go through the plane of the galaxy. As now the light from these images aren't just interacting with the whole galaxy as a whole. They're now interacting with pockets of matter and stars and pockets of dark matter as they pass through the plane of this galaxy. And so all of these smaller objects act as their own lenses, known as microlenses. So typically, when you have an object pass between you and a light source, it'll act like a magnifying lens. Just like passing a magnifying lens between you and a candle, you'll see an uptick in brightness as it goes along. And so if you're to draw a light curve, which is a plot of brightness over time, you would see an uptick in this brightness of the light source. Now what happens when the light of the quasar images is passing through the disk of the galaxy, and it's not just interacting with the whole galaxy, it's interacting with all of these different smaller lenses. Now, that's like saying you are putting a bunch of different magnifying lenses between you and a candle, all at different times, and you get a much wider variability in your light curve. And this variability is a function of many different things, but most importantly, it is a function of the size of the light source, or the size of the emission region of the light. So let's get into our system. Our system, SDSS 1339, is a doubly lensed quasar. So here, these images are taken from ground-based telescopes, that's why they're a little blurry. But you can see clearly there's a foreground galaxy in the center, and it's microlensing a quasar, 1339, behind it, and we see them as two separate images, A and B right here. And these images are passing through the disk of the galaxy, so they're being microlensed by this galaxy. So let's get into my project. My project broken down to 3 phases. The first phase was creating the light curves, so the plots of brightness over time, first in the optical wavelengths, so the visible wavelengths, and then also in the X-ray wavelengths. And then also modeling our foreground galaxy, and putting these together to create simulations that create simulated light curves and comparing them with our observed light curves. First in the optical, and then supplementing them with X-ray light curves to create a joint analysis. So phase 1. So the idea for this project first began in 2021 when my advisor and his colleagues, Professor Christopher Morgan, looked at this plot right here of SDSS 1339. This is a light curve of 1339 in magnitude units over time. So magnitude units are logarithmic units where lower numbers indicate higher or brighter observations. And they noticed that there is a lot of variability. Now, this variability is mostly intrinsic to the quasar, because remember, quasars are inherently brighter and dimmer over time. However, if you were to take the light curve of one of the images, let's say image B, and then offset it by the time delay of the system, and then divide it out with image A's light curve, you get what's called a difference light curve, which is on the bottom. And this tells you the variability in light due to only the microlensing effect of the foreground galaxy. So they thought this would be a great candidate to study in X-rays. And so, and this was perfectly in time for my Trident project. So the first thing we did was create updated optical light curves. And so these are updated optical light curves with 3 new seasons of optical observations using the Nordic Optical Telescope, or the NOT, and the Liverpool Telescope. And then we also wanted to study these objects in the X-ray wavelengths. So my advisor proposed, and it was accepted, that we receive 4 epochs of observational time using the Chandra X-ray Observatory. It's a satellite X-ray observatory in space. And now 4 observations doesn't sound like a lot, but it's enough to create a light curve. And each of these observations lasted about 32 kiloseconds per observation, which for a total of about a full day of just staring at this object. And we had to look at it for so long because X-rays are so rare in the universe that you just have to stare at an object because the photons will hit Chandra so infrequently. So that is what we did, and we received the data from Chandra this year. And we receive it like this. We receive an image of SDSS 1339, and you can see there's 2 clear, distinct images, A and B, of the images. However, there's a blooming effect, so that they don't just look like point sources anymore. They kind of bloom out from their center, and there's even a blending effect of the images in the middle. But we want to know how many photons are coming from image A and how many photons are actually coming from image B. So we have to model over this, what we call point spread function modeling, or PSF modeling, to understand how many photons are actually coming from each image. Now, for that, I got to rely on the expertise of Dr. Sinyu Dai at the University of Oklahoma, and so I got to spend a week last semester at the University of Oklahoma. It was awesome. It was amazing. This is me at OU, and there I learned how to create X-ray light curves and analyze these images. And now a cool thing that Chandra can do is it can distinguish the photons that hits it by its energies. So it remembers the energies of each photon that hits it. And so you can create plots of photon count rate as a function of their energies. And you can see here how slowly a photon will actually hit Chandra. So this is photon count rate of around 10 to the negative 3 photons per second that's actually hitting Chandra. So very, very rarely is a photon actually hitting our telescope. But because with that, we can bin our photons into separate bands. So what we did was we took 4 different bands of energies. First, a full band, so the entire range of the X-ray spectrum that we are looking at. And then a hard band, which is the higher energy photons. And then a soft band, which is the lower energy photons. We also took an iron band because the system has a very strong iron emission line, and we wanted to look at that on its own. And with that, we created our X-ray light curves. So these are the raw X-ray light curves of image A and of image B. And again, we want just the difference light curve. So we offset one of the light curves by its time delay and divide out to create our difference light curve. And this tells us the variability in the X-ray observations due to just the microlensing effect of our foreground galaxy. With that, let's get to phase 2, which is modeling our foreground galaxy. So we don't know the exact makeup of our foreground galaxy, so we don't know the exact effect that the microlensing is having on each of these images. So what we have to do is we have to model this. So we create 10 macro models of our galaxy, spanning the entire range of what we would expect to see in our lens. And then with this, we create magnification patterns, which are 2D projections of the total magnification along a certain line of sight. And so we take 400 magnification patterns for image A and 400 magnification patterns along the sight of image B. And again, they span our reasonable expectations as to what the total summation along a line of sight would be for our magnification. And then with that, we run Monte Carlo simulations in which we pass a model quasar across these magnification patterns, and we create simulated light curves. And we change a bunch of different parameters, one of them being velocity, one of them being the trajectory of the quasar. But most importantly, we change the size of the quasar. So we change the size of the emission region, or the size of the light source of these objects as we pass it across the magnification pattern. And we run about 10 to the 8 trials. We throw everything but the kitchen sink at these magnification patterns. And with 800 billion magnification patterns, that's 800 billion simulations that we are running a model quasar across these magnification patterns. And so for that, we use the USNA high performance cluster. Now, most of these simulations are thrown out immediately because their simulated light curves do not match our goodness of fit for our observations. And Bayes' theorem says that simulations that more closely match our observations are more likely to be physical realities. But we kept about 2 million successful solutions running it in the optical or the visible wavelengths. And when we further constrain that into our X-ray wavelengths, we got about 20,000 joint successful solutions. So here are the 5 best Monte Carlo simulations in the black lines compared with our optical light curves. And you can see here there's a lot of variability. There's about 0.5 magnitude change, but it's over the course of 5,000 days. So it's still a good amount of variability. 0.5 magnitudes is a good amount. Remember, this is in logarithmic units. But when we looked at we compared them with the X-ray wavelengths, the X-rays are changing by about a full magnitude in as little as 100 days. So the X-ray source size is most likely much smaller than the optical source size, because as smaller objects pass along the magnification pattern, the whole thing will be magnified, right? So it'll be your variability in your light curve will be much greater, and so it basically tells us that our X-ray sources must be much smaller than our optical light sources. So our primary result is in the form of probability densities, and these are plots of probability as a function of the size of the emission regions. And you can see here the vertical lines represent the Schwarzschild radius of the black hole, so that's the event horizon of the black hole. Anything below the event horizon must fall into the black hole. And the ISCO, or the innermost stable circular orbit of the black hole. So anything below this won't have a stable orbit and will either be falling into the black hole or be knocked out of it. And the black curves represent the optical emission sizes, and the blue curves represent the X-ray emission sizes. And the peaks are our expectation values of our answer. So basically the expected value of what the size of these emission sizes are. Now the hard band, you can see, is we weren't able to constrain it. There was too much signal to noise when just looking at the hard band. So we really just looked at the full band X-rays. I don't know what that was. But you can see that the X-ray source size is very, very close to the event horizon of the black hole. So it's very close to the gravitational radius of the black hole. It's within the ISCO. It's within the innermost stable circular orbit of the black hole. It's about 3 gravitational radii away. And so this tells us a few things. One of them being that the black hole is probably spinning at a very significant rate, probably very close to its maximum angular momentum, because as black holes spin, their event horizons and their ISCOs will reduce down close to the gravitational radius of the black hole. And so a lot more interaction of matter can happen closer to the black hole. But the biggest thing is that the small source size basically rules out our disk corona model, our older, more conventional model that says that X-rays can be created as far out as 200 gravitational radii, and favors newer models like the lamppost model that says that X-rays can be created created very close to the center of the black hole at around 3 gravitational radii. So this is a very, very significant finding. Basically answers this decades-long debate and throws out the older model. So in this, we will be publishing these results in a paper in the Astrophysical Journal soon. So a little summary of what my project was. We have these things called quasars, and we think they're accretion of matter onto supermassive black holes. However, they're too small and they're too far away for us to really just take a picture of them. So we need to employ something called gravitational microlensing in order to understand them. And we need to simulate that microlensing effect and compare our simulations to our observations, where we create probability densities to find the size of the emission regions. And then with that, we basically ruled out the older, more conventional model in favor of newer models. And that is my presentation. So any questions? Yes, hello.
In the middle slide you have, am I looking at theoretical curves versus what you have computed? What are the dashed versus the lines?
Oh, so the dash lines, I'll go back. Sorry. So the dash lines are with mass priors, which basically means first looked at them, assuming that the average microlens, the average object in the lensing galaxy, is between 0.1 and 1 solar masses, so around the size of our sun. And then we ran it without any mass prior, so where the microlens can be any size. And we typically want the simulations with no mass prior and the simulations with mass priors to be roughly the same, because we expect the lenses to be around the size of our sun. Yep.
What you have on the vertical axis is the derivative of something?
Yeah, it's basically the probability. It's normalized to 1, so it's the probability of taking a point and saying what is the probability that the size of this emission region is this size. So the peaks of these curves are our most expected value of the emission size. Any other questions? Yes, Professor Knight.
Great job, Jamie. When you're modeling, you're modeling of the path through the lens galaxy, are you modeling something specific like stars or solar systems, or is it just kind of a generic change of mass or some sort of path through it?
It's really just modeling it's modeling a bunch of different things. So it's modeling things called like shear and convergence of the system, but it's really modeling just like specific objects. So like stars and like pockets of more dense matter and pockets of more dense dark matter as well. And then there's a function that runs it and creates a magnification pattern based off of like the shear or the warping of space-time due to these objects. Yes.
You were looking at these two different explanations, and were able to eliminate one of the explanations. Were you able to do a hypothesis test to eliminate this explanation? And were you able to get a p-value from that?
We weren't. We basically were just looking at what is the size of the emission region, and if it's much smaller than some models, those models are probably wrong. And if it's very large, then maybe those models are correct. Yeah. Yes, sir.
Thank you for your presentation. A fascinating project. You mentioned the secretion process. Is that an ongoing process that's happening with like a rate that has to be accounted for, or are you able to think of a quasar as a static object?
We can basically think of quasars as static objects because these quasars are in very young, distant galaxies, so there's an abundance of matter. So we don't really see a change in the amount of matter that's spinning around the black hole over time. These are just like astronomical units. They will take billions of years to actually fully disappear. Yes.
How long did it take to do the 80 billion simulations?
The 80 billion simulations took about 2.5 weeks, I think like 20 days. We first started, we wanted to make sure the simulations actually worked properly, so we would only run like 1,000 or like 100,000 simulations at first, and those took like an hour. But like our full analysis, when we fully ran it, was about 2.5 weeks. I think it was about 20 days.
There are no other questions. Let's thank our speaker again.
Thanks, guys.
you a little bit more about some of their projects. We're going to continue with Sam Shin from the 13th Company. He's from Northbrook, Illinois. His service assignment is Navy pilot. But before that, he's going to pursue a master's degree in statistics at the University of Oxford. He's also a member of the Glee Club.
Thank you. Good morning, everyone. My name is Sam Shin, and my Trident project is titled A Fast First Order Method to Calculate the Low-Loss Theta Function. So today I'm going to introduce the project and the motivation behind it. I'm going to walk you through how I reformulated the low-loss theta function into a structure that lets us apply gradient descent methods, and I'm going to discuss the computations behind this process. Then I'm going to summarize the algorithm as well as the findings of our project. Our project lies at the intersection of numerical optimization and graph theory. So a quick brief overview of graph theory. A graph is a set of vertices and a set of edges. So this right here is a very simple graph. The blue circles are the vertices, and the black lines that connect them are the edges. Graphs are a ubiquitous model. They're used in neurology, transportation, the internet, and basically every form of engineering and science. And they're used to model relationships that exist between discrete objects. So the vertices, the blue circles, they represent the objects of the model, and they are connected by an edge or a black line if there exists some sort of relationship between those two objects. A graph invariant is a property of a graph that's independent of the graph's physical representation or labeling. So the canonical example of a graph invariant is the order of a graph, which is the number of vertices. The order of the graph here is 6 because there are 6 vertices. It doesn't matter if you label them differently. If you extend 3 all the way out there, if you flip the picture upside down, there's always going to be 6, so the order is 6. And algorithms to compute these graph invariants efficiently are a major focus in graph theory and research. So because graph invariants are independent of the physical representation, we can use them to understand some of the more abstract structures behind certain graphs. One interesting graph invariant is called the Shannon capacity of the graph. And the Shannon capacity is a measure of how quickly a confusability graph G can communicate information with 0 risk of error. I'm not going to talk about the nitty-gritty of the definition of the Shannon capacity, but I'll explain what it means with the Pentagon graph C5, or the 5 cycle. So imagine a language system, a writing system, where the symbols that you're allowed to use are 1, 2, 3, 4, and 5, so the vertices here. And 2 symbols can be confused with each other if they're connected by an edge. So let's say I want to say 1, but because 1 is connected to 2 and 5, you might hear that as 2 and 5, and the same goes for all of the other vertices. The Shannon capacity of C5 has been proven to be the square root of 5, meaning that the language that's modeled by the Pentagon can send at most root 5 messages per time step with 0 risk of confusion. So it's a very interesting graph invariant that has applications in information theory and security. However, it's extremely hard to compute. In fact, the computational complexity of the Shannon capacity still is an open problem. So we know that the Shannon capacity of C5 is root 5, but by adding just 2 more vertices and getting the heptagon instead of the pentagon, that becomes the most famous open problem in information theory. A well-known approximation for the Shannon capacity is called the low-loss theta function. The theta function was introduced in 1979 by Hungarian mathematician Laszlo Lovász as an upper bound on the Shannon capacity. So it bounds it from above, meaning that it can be applied to a variety of different networks that communicate across noisy mediums to evaluate the speed and the quality of those networks. So because it bounds the Shannon capacity, the theta function has applications in classical information theory, but its real relevance today is that it's been generalized to what's called the quantum Lovász number. And it's now being used to evaluate the quality of quantum channels in quantum information theory. Another interesting application of the Shannon capacity, or the theta function, is that it bounds the clique and the chromatic numbers of a graph, which are 2 important but NP-complete graph invariants. NP-complete means that efficient algorithms to compute the clique and chromatic numbers are unlikely to exist unless P equals NP. So the theta function can be modeled as the optimal value to a semi-definite program, or SDP, meaning that it can be computed in theory in polynomial time. SDP is a class of convex optimization, where the objective is to minimize or maximize a linear function of a symmetric matrix over the intersection of an affine hull with a cone of positive semi-definite matrices. However, solving STPs is inefficient in practice. The theta function in particular has a massive polynomial scaling, so just by increasing the size of the graph G slightly, the runtime to compute it through interior point methods explodes, basically. And interior point methods for the theta function fail on graphs of even just 100 to 200 vertices in calculating the theta function. So the goal of this project is to approximate the solution to the theta function which is a large, complicated optimization problem, and we want to decompose it into a series of iterative small subroutines that are much more efficient to do altogether. And we want to prove that this specific iteration approximates the theta function accurately and efficiently. And the method we have chosen to do this is called accelerated projected gradient descent. Here you see the formal definition of the theta function. So we're operating on an undirected simple graph G with vertex set V and edge set E. The theta function is the solution to the following STP. We're maximizing the inner product Jx subject to trace of x is 1. And if vertices I and j are connected by an edge in E, then the ijth element of x is 0, and x is positive semi-definite. And j here is a matrix of all ones. So imagine that G has n vertices and blue circles, and then we have an n by n matrix. We want to maximize the sum of each element of that matrix. However, certain elements, the edge elements, are going to be forced to be 0. The trace is 1, meaning that the diagonal elements have to be summed to 1. And then that last symbol there is positive semi-definiteness. It's a generalization of non-negativity to the space of symmetric matrices. And x being positive semi-definite essentially means that the eigenvalues of x are non-negative. So previous work has shown that positive semi-definiteness, that last inequality constraint, is best enforced implicitly via penalties, whereas equalities, so that's going to be the trace constraint and the ij constraint, those are best enforced explicitly with projection. So now the first goal of our project is to split the theta function up into two parts. We want to enforce the positive semi-definiteness with penalties and then explicitly enforce the equalities. We do that with theorem 1. So theorem 1 states that the function f of x equals jx plus min over y positive semi-definite of xy is concave. And if x is positive semi-definite, that function is exactly jx. If x is not positive semi-definite, this function is negative infinity. So this is what we call a partial Lagrangian dual. So by adding the min over y positive semi-definite of xy to the objective, this implies that x must be positive semi-definite. We don't actually have to say that x is positive semi-definite, but if it were not, then f of x is negative infinity. And because our problem is a maximization, we're maximizing f of x, so we would not want that objective to be negative infinity. Therefore, we see that an optimal solution is found only when x is positive semi-definite, because then we get the objective to be jx, which is the original objective. And lastly, we want to apply projection to enforce the equality constraints. So let R1 be the space of symmetric matrices with trace 1 that also enforce the edge constraint. Notice that R1 is simply the feasible region of the original theta function, just not including the positive semi-definiteness constraint. And this gives us that the theta function is exactly equal to the maximum over x and R1 of f of x. We force x to be in R1 so that the equalities are constrained properly. And then because f of x contains that Lagrangian variable, y, that enforces a positive semi-definiteness. So to this problem, we want to apply what's called gradient descent. Gradient descent is an iterative first-order algorithm. Basically, at every iteration, it calculates the gradient or the derivative of the function, and then it travels in that direction because that's going to be the direction where the function increases the fastest. And it's a simple and easy way to optimize a problem. However, because j is not positive semi-definite, our problem is not differentiable. It's a jagged function, so we can't find a derivative at each iteration. So what we do here is we apply a procedure called Nesterov smoothing. So first, let dual constraint U with J, the almost matrix, and we bound the trace of U to be n to the 4.5. So Q1 is going to be the compact primal set, Q2 is the compact dual set. And D1 of x is a differentiable, strongly convex prox function of Q1 with parameter sigma. And the simpler that we can choose D1x, the better our approximation is going to be. So recall that f is the objective of the original theta function, and let f eta be the objective of this approximation. So basically, that whole thing, not looking at the min. So it's just going to be the max over x in Q1 of yx minus eta d1x. And denote by x of m of y the solution to f eta of y. This brings us to theorem 2, which is our biggest finding, or one of our biggest findings of the project. And it states that the function f eta of y is well-defined, convex, and continuously differentiable at any y in Q2, meaning at each iteration it is possible to calculate a gradient. and its gradient, the gradient of f beta of y is equal to the solution of the inner maximization. It's exactly equal to x m of y. And this gradient is Lipschitz continuous with constant 1 over eta sigma. Theorem 2 states that for an eta positive, the function f beta is a uniform smooth approximation of f, meaning that the limit as eta approaches 0 of f beta equals exactly f. So altogether, this is our reformulation. We're minimizing over Q2 the maximum over Q1 of yx minus eta d1x. Q1 is the smooth primal set, Q2 is the compact primal set, Q2 is a compact dual set, and at each iteration, y in Q2, the gradient is a solution to the smooth primal problem, max over Q1 yx minus d1x. So here's our result. It's a differentiable uniform approximation for the theta function that has a compact feasible region and a computable gradient formula. So computing that gradient is the next step. Essentially, right now we're just trying to find the derivative in a very fast, efficient way. So we're going to fix a y in Q2, and then we choose the quadratic box function for the primal set. And I'm just going to run through this. It's a very complicated proposition, but it comes out to be pretty simple at the end. So first let u equal y minus j, and let little u be the diagonal vector. And then we're going to compute z1 we're going to compute each zi by sorting u into a decreasing order, and then finding the row, which is going to be the max index that satisfies this complicated positivity condition. And then using that row, we define theta. And lastly, zi is going to be the maximum of uii over 2 eta minus theta, or 0. So whichever is greater of the two. So here's our proposition. The gradient, the derivative at each iteration y, is going to be the matrix that's formed by this. It's 0 on the edges, it's zi on the diagonals. On the non-edge, non-diagonal entries, if the condition eta is greater than or equal to 1 plus uij over 2 is satisfied, then the element corresponding to that is 1 plus uij over 2 eta, and all the rest of the matrix is just going to be 1. Note that this is not closed form. So zi is calculated by this algorithm, which is not a closed form solution. However, the slowest part, the bottleneck of this is number 1, sorting u into decreasing order. And that's a very fast procedure. Sorting can be done in linear time, meaning that the dual gradient can be calculated very quickly in linear time. And we're going to denote this by xn of y. We also want to find the primal gradient, so we can calculate the duality gap later on. So for this, we're going to let u be a positive smoothness parameter, and the primal gradient is a solution to the smooth dual problem, which you see on the screen. So the idea behind Nesterov smoothing is that we have a dual problem and a primal problem, and the solution to the dual problem is a primal gradient, and vice versa. The solution to the primal problem is a dual gradient. And we're going to choose a spectral entropy prox function for the dual space, which is each eigenvalue multiplied by its own natural log. And we can prove this following proposition. The primal gradient at x is the matrix n to the 4.5 of the matrix exponential of x divided by mu times the trace of that whole matrix. And we're going to denote this by y m of x. So now we have a smooth problem over compact sets and fast gradient calculations. We proved using the appropriate Nesterov theorem that the complexity of solving this smooth problem is on the order of n to the 2.25 over epsilon, which is significantly faster than using interior redundancy to calculate the data function exactly. So we're sacrificing some epsilon accuracy. It's going to be slightly less accurate than doing it exactly. However, it's going to be n to the 2.25 faster than that. And we're going to define an epsilon saddle point. So we're going to call x bar y bar, where x bar is in Q1, y bar is in Q2. We'll call it an epsilon saddle point if this following condition is met. So we're maximizing minus the minimization. We can smooth out this whole middle term, and we're going to call that psi the duality gap. And that duality gap can be computed exactly and quickly using xm of y bar and ym of x bar. There's many different types of gradient descent. There's standard gradient descent, proximal, but we choose to use what's called Nesterov accelerated gradient, which is considered to be the fastest and the simplest way to apply gradient descent. So we're going to apply Nesterov accelerated gradient, NAG, on the smooth problem until we reach an epsilon saddle point for the smooth problem. And by the proposition, or the theorem that states that the smooth problem is an exact uniform approximation for the actual problem, we're going to treat the saddle point as an epsilon saddle point for f, the original objective. This brings us to the following theorem. We're going to fix epsilon to be positive, and that's the accuracy that we want to achieve. And we're going to let x bar, y bar be an epsilon saddle point for non-smooth approximation. Then this following iteration is an epsilon solution for the theta function itself. And that can be done almost instantaneously by calculating the value. So now we apply Nesterov accelerator gradient to find an epsilon saddle point for f eta, the smooth approximation. We can treat that as an epsilon approximation for f. And then we're going to apply this projection algorithm right here to obtain an epsilon optimal solution for the theta function. So we have gone from a solution to the smooth function, and we can almost instantaneously round it into a solution for the actual function that we want to solve. And this is the whole algorithm. I won't walk through each line, but the top two lines right there are just initializing the parameters. And then you see we loop through the Nesterov acceleration algorithm until we reach a duality graph that's less than epsilon, which is the accuracy we want to achieve. And then we check to see if the minimum eigenvalue is positive or negative. If it's negative, we apply the projection. And our output, we have proven, is an epsilon approximation to the theta function itself. So we apply Nesterov accelerator gradient and projection to find an epsilon optimal solution for the theta function. Our report also includes a MATLAB framework for this algorithm. And our future work is going to focus on fine-tuning this code. We want to fine-tune the stability parameters so that we can achieve that desired speed. So there's the theoretical bound on runtime, which is n to the 2.25 over epsilon. However, we find that the code doesn't actually achieve that because there's so much stuff going on within the computer that's different from what can be proven on paper. So first, we're going to approximate the matrix exponential. The matrix exponential is an expensive computation, but we can approximate it. It's been proven that that can be approximated to an accuracy that's sufficient for the Nesterov algorithm. And then we're going to find a way to auto-adjust eta and mu, the smoothness parameters, in an optimal way to achieve epsilon accuracy. So in summary, we were able to decompose the theta function into a series of simpler subroutines. And our major results were a continuously differentiable approximation for theta, a sorting algorithm for the dual gradient, a matrix exponential solution for the primal gradient, and then finally a linear projection that rounds epsilon saddle points for the approximation directly into epsilon optimal solutions for the theta function. And our novel contribution here was that we penalized the positive semi-definiteness. Previous work, it penalizes the inequalities and then explicitly enforces positive semi-definiteness. But by switching the scheme, we were able to efficiently compute the gradient because we were only working on individual matrix constraints. And this reformulation scheme can be easily applied to any other SDP because every semi-definite program is going to have the X positive semi-definite constraint. But the computations, they relied on the specific constraints of the theta function, showing, in general, that we can penalize positive semi-definiteness. However, to find fast first order algorithms, you have to exploit the specific structure of the specific SDP that you're working on. So there's no real general way to apply our method to the whole class of semi-definite programs, but you can pick something that you're interested in and pretty easily compute gradients and then apply it to come up with first order methods. And now our goal is to translate all of this theory, all of the theorems and propositions into an open source tool that researchers can use to quickly calculate the theta function for large graphs. And hopefully this, in the future, will have some sort of impact on the development of quantum information science. Here are references. Thanks so much. Yes, sir.
A couple of questions, but before that, I hope the math department is planning to hire you in place of some of us full-timers. You mentioned something about sort of like with the jamming capacity that people are able to see by. Do you have any good idea about how thinking that sort of like should be that number?
Yes, sir, I do actually. So, the appendix. So the question is, how much information can a graph transmit with no error? So again, here's C5, the Pentagon graph. So, like I said, 1 can be confused only with 2 and 5. It can be differentiated from 3 and 4 because they're not connected by an edge. So let's say you can send one symbol per time step. Then we can only send 2 symbols that cannot be confused. So let's say 1 and 4. Because if you also want to say 2, 3, or 5, that's going to be connected to at least 1 or 4. So with 1 time step, you can only send 2 symbols. But then if we lengthen the word to 2 symbols, we can find 5 words, 1, 1, 2, 3, 3, 5, 4, 2, and 5, 4, that are not confusable. So for example, that's because 11 and 35 are not going to be confusable because 1 and 3 are not connected. The first symbols for each of these words are not connected. And what Lobos proved is that this is the optimal solution. Making the words longer into 3, 4, 5, 6, it doesn't actually add any sort of benefit to that. So because we can send 5 words in 2 time steps, that's going to be, so each message takes 2 time steps to transmit, because we can send 1 symbol per time step, and we can send 5 to the n over 2 messages in n time steps, just by, because there's n combinations. So that means that per time step, we just take the nth root, which gives us root 5 messages. I don't know if that answers the question. It's not really intuitive for me either, but it's just a matter of experimenting and improving that it's about as good as you can get.
So did you apply your algorithm to C7 just to see what's the conjecture for C7?
What we found is that the result for C7, in our code is far from complete. It varies wildly depending on what you set eta and mu to be, which is why we want to come up with a way to auto-adjust eta and mu so that we always achieve epsilon accuracy.
I just have a comment. I just wanted to express how your excellent command of mathematics is shown every which way. It is absolutely exciting to see how one can have such a great command of such a complex and theoretical subject. So for all the Tridents and future Tridents, this is the way to go. Like get the depth of that understanding of mathematics you have at hand. You are right. This is an excellent presentation.
Thank you. Yeah, the hardest part of this whole thing was trying to make it presentable, I guess, because even I don't really understand what I did. But I mean, I think that's really the beauty behind pure mathematics, is that pure mathematicians don't really care about the applications. Luckily, we have an application here, but they just do it because it's beautiful, and just keep doing it, and maybe in 100 years, scientists will find some sort of application for it. So it really got into the weeds with this project, and learned a lot from it.
today. Our next speaker is Adrian Boucher from the Naval Company. He's from Atlanta, Georgia. His service assignment is Navy pilot. In the fall, he'll be attending Stanford University for a master's degree in aeronautics and astronautics and continuing his rowing career.
Morning, everyone. I'm Adrian. I hope everyone is as caffeinated as I am because I'm going to do my best to attempt to break this down Barney style. So essentially, when we look at the title of this presentation, our end state goal was to essentially develop a flying version of the Tesla autopilot for drones, using a camera to be able to look at a ship and autonomously guide in a drone in for a landing. I was told I should probably include this. This is not the official position of the DoD or the Navy. These are just my opinions and things I've learned along the way. So that being said, this is what I actually wanted to call this presentation. This is the reality of engineering. You have hardware in the critical path, and we try again, and we learn a lot on how not to do things so that the researchers that will pick this up don't make the same mistakes we did. So spoiler alert, we did not get to our end state, but we learned a lot along the way. So why are we trying to do this? So according to the CNO, the Chief of Naval Operations 2022 NAV plan, by 2045, the Navy is looking to integrate over 900 unmanned assets as teammates. So we have our rotary wing systems that we're looking to integrate rotary wing ISR platforms, that's intelligence, surveillance, and reconnaissance. We have tactical aviation teammates with the X-47 uncrewed combat aerial vehicle and the MQ-25 Stingray as a air-to-air refueling platform. So we're looking to integrate these unmanned systems that are very reliant on GPS and radio frequency communications. The Fire Scout here uses a system called UCARS, or the UAS Common Recovery Aircraft System. So what that entails is a two-way radio link in order to bring in the unmanned system for precision landing. And that is not covert. You're broadcasting your position to our potential peer adversaries, and they have it's a vulnerability where they could deny that service through jamming, and our GPS sensors, they could be spoofed by our peer adversaries and with malicious intent. And thus we need to fortify these systems through passive means that don't rely on these radio frequency-based sensors. And additionally, the Navy and Naval Aviation has a process for certifying manned systems. But what is that going to look like for unmanned systems? It's still a very emergent topic that we're invested in solving, which is why the Office of Naval Research has founded this SAILOR initiative, and that's for Shipboard Autonomous Launch and Recovery. We're looking to find new solutions. It's a collaboration between the Office of Naval Research, the Naval Air Warfare Center Aircraft Division, George Washington University, and USNA. Working to find a working solution to this. So the Navy, the Naval Academy is in the unique position of operating these 108-foot yard patrol craft that I know all the mids here are all too familiar with. They're for the training of rising naval officers, but one of them, through the sponsorship of ONR, has been repurposed with a flight deck. And previous Trident researchers have investigated the aerodynamic air-wake interface through wind tunnel testing and CFD, and we're looking to use this same platform to do our unmanned system research because essentially it models a quarter-scale destroyer and is a lot cheaper and more flexible to utilize for this testing than getting the operational requirements to get a whole destroyer out and test the systems that we're investigating. And a project that I worked on a couple years ago was the dynamic interface. So we had our operator flying a drone manually and seeing what different approach paths, which ones were the most difficult, like quantifying the handling qualities. And this would contribute to future path planning for our unmanned system recoveries. But we're looking to build upon that. We were looking to build upon that with this Trident project. And our mission at the outset was the autonomous shipboard landing, as I discussed, using computer vision methods, cameras finding the ship, coming in and landing. But when Commander Costello approached me about this, I was all fired up, and it's like, yeah, we're going to get there. We're going to do the experimental setup. We're going to do all this research. It's going to be great. But when we look at technology readiness levels, GWU has a system like this that they're getting up and running and doing tests with. But at the Academy, because we're limited by what's called NDAA, or the National Defense Authorization Act, there's a lot of hardware out there that's made by our peer adversaries that we can't use. And GW has the flexibility to use that, and we don't. So we need to develop a platform that will enable us to conduct this emergent research, certify systems, but using hardware that we are authorized to use. So in terms of readiness levels, we're about a 1 or 2 conceptualizing this testing process, and doing the full up autonomous flight testing would be around a 6 or a 7. And spoiler alert, we're getting to the lab testing that we did during this project puts us about a 4, where we're testing the subsystems in the laboratory and laying the groundwork and foundation, which ultimately changed the mission of this project to establishing procedures, hardware, software, safety practices, so that the next researchers that'll pick this up don't have to go through the same mistakes, and we can make progress towards certifying these systems. So that everyone's on the same page for the concept of operations, or CONOP, of what this integrated flight test is looking like, what our end state goal would be, is taking off from the hospital point in a manual flight mode, going over the Severn, activating the computer vision system as the YP, specifically YP689 with that flight deck, is underway. And then it would conduct the autonomous approach using the methods that we've been developing, and using what's called RTK, or real-time kinematics, as a differential GPS system. So GPS module on the boat, GPS module on the drone. The difference between them can be centimeter level accuracy. And that will lay down our ground truth for performance testing. Now, we didn't get the RTK system working, which is part of the reasons why we never got there, but we'll get into that momentarily. Here's another visual side-on profile where you can see the camera. The idea is that we have the camera field of view on the drone looking at reference markers and different shapes on the ship to identify where the drone is relative to our target, so we can feed that information to the flight controller to do our guidance, navigation, and control for that precision landing. So how do we get there? Well, the answer is, first we got to identify what specific methods we're going to use, which I'll get into momentarily. Lots of lab testing. We have a safety net like drone flight labs down here, because propellers are not friendly to fingers. And also, we're very concerned in the airspace that we operate in, the CIFRA, or the airspace that surrounds DC, like we cannot afford to have a flyaway of our drones. So we need to do a lot of lab testing to ensure that is not going to happen, iron out all the issues. And yes, safety. And you do more testing. And you do lots of troubleshooting, which is what 90% of my time was. Then you do more testing. And then you rehearse. And then you land on a simulated target, like a pickup truck with a marker on it that simulates the target vessel. You rehearse, and then maybe you get to go test it on the boat. So that is where I wanted to be at the end of the semester, at the end of this year. And we did not get there, but we learned a lot along the way. But technically, what that means is for the characterization of the performance of our computer vision methods, there's 2 avenues that we looked into. That's implementing fiducial markers. So you can see that essentially it looks like a QR code. It's a well-documented method for estimating the pose, or the relative position and orientation of a camera from this marker. And we were looking to repurpose an existing system to be able to test and implement in this emergent field for Navy operability. No need to reinvent the wheel. But additionally, we also wanted to look into using convolutional neural networks, or different AI methodologies. So that marker, practically speaking, can never be bigger than the ship itself. But what if we can just see the ship and then get a machine learning interface trained on how to identify it? We can do some servoing, hone in on it, and get close enough to see the markers to come in for that precision landing. And then we have to integrate. Big part of this project is the integration of that computer vision system to the existing flight control hardware and software. And this is where we got stuck. And then after that, we get into the flight test in motion capture lab, ironing out, as I discussed before, and then we go test it. So let's get into some mathematical principles behind our model that we're using to get that pose estimation off the markers. So it operates under the pinhole camera model, which is a unifying way. It's a unifying method to relate what we observe in 3D space onto a 2D image projection. So what we're looking at is these X and Y components. It represents that blue point out there. It's where things are actually located in 3D space. That U and V is the pixel location on our image plane for our camera. This matrix right here is what we refer to as the intrinsic matrix, which is the focal length and the principal point. And this relies that we're not changing our focal length, so having a fixed focus lens for our camera was crucial. Otherwise, you have to account for every possible focus, which is it's not going to happen. So we find this through camera calibration, which I get into in a moment. And then if you know those three things, if we have a known object, and then we observe where it's located in the frame, and we have the intrinsic parameters, we can get this rotation translation matrix, which will give us our XYZ rotation translation relative to that known point, and the orientation of our drone, which is ultimately what we're looking to do and provide the flight controller to make that guidance, navigation, control decision making. So this is ideal. And no lens is actually ideal. So any lens or camera system is going to have some sort of distortion. So what we did is we took a bunch of pictures of a chessboard matrix like you see right here, and in different orientations, and the software observes how that chessboard of known dimensions, known size, is deformed, and then spits out our intrinsic matrix and our distortion coefficients, which we use to get a more precise estimation of that pose. Going into Aruka pose, so essentially, as I discussed before, these like QR code looking structures, and using some line detection methods, we identify the corner and the side length, and if we know the dimensions, like the pinhole model that I explained before is a known point. If we have an object of known dimensions, we can use that to identify the pose of the drone itself. And the entire basis of the project is feeding those 6 values to the flight controller to make those guidance, navigation, and control decisions. So roll, pitch, and yaw, and our XYZ translation. And an extension to what we investigated is implementing these machine learning methods. So this is a very wave-tops explanation of what a convolutional neural network is. I believe it's outside of the scope to go into architecture, but essentially, if we feed a bunch of images of a boat and we label it, this is the boat we're looking for, this machine learning model can identify that, yes, this is in fact the boat. And what we want to do is correlate different aspects and ranges away from the target vessel with known position information. And so eventually our neural network model will be able to estimate broadly where the drone is, servo in, hone in on the target vessel, and transition to that Aruka method, which is computationally simpler and is more well documented. So, getting into the hardware of what we use, the Naval Academy has developed this X8 octocopter. It has a 15-pound payload, 25-knot crosswind limit. We've been using it for that dynamic interface research I talked about. But as Commander Costello told me early on, we're not losing $15,000 if we drop it in the drink. So, call sign Bucket Fighter, I've built the Pail Fighter. So it's a flight control copy of this, but a lot smaller, it's an expendable asset, so we can test like the different computer vision methods at relatively low cost. Our computer vision payload consisted of a Raspberry Pi computer board and a Luxonis Oak D depth sensing camera. So getting into compliance, so there are a lot more powerful computing assets out there, like the Jetson Nano, that we simply can't use. And so on hand, we use this Raspberry Pi and this Oak D. Recently found out that the Oak D is also not compliant. So we're gonna have to work to figure that out. But this is a good, like, we're using known hardware and repurposing it for our solution. And the capabilities of this Oak D and these depth sensing cameras in general is that they can run these neural network models that I talked about natively, which will save like computational load, and then they will be interpreted by the companion computer and then relay that information to our flight controller. And the idea is that we don't have to reconfigure anything that's going on in our flight controller. We can feed it information that looks like GPS inputs, but really we're more or less spoofing our own controller to get new information through a passive method. Next up, the Maritime Autonomous Guided Intelligent Coupled Systems Laboratory. Say that 10 times fast. So I worked here 2 years ago on an internship, and at that time they were building a 1/10 scale model of the YP with a flight deck so that we can conduct training exercises in our laboratory environment, reduce risk, and conduct testing with motion capture. So we threw this into the motion capture lab at Naval at their office in at Patuxent River, and motion capture, to explain broadly, is we use an array of infrared cameras and infrared emitters, and we have an array of markers on our target vehicle, so drone and the ship, and we can know the ground truth exact position between the two, and then we can compare that to the computer vision estimate so that we can evaluate the performance of the methods we've selected. So initially, we looked into sizing, because although this is not necessarily novel, we need a framework for the hardware we've selected to push this work forward. So printed out marker of 1 meter side length and 16 centimeter side length to observe the max range capable with these marker sizes. And documentation indicates that in order to do our autonomous landing, we need a minimum of a 10 hertz feed rate to our flight, so 10 pose estimations per second feeding to our flight controller. And so what we did is we had the computer vision system on the small UAS, started it right up against the Arucos, and then backed it out and looked at the data to see what our max range is. And we implemented a flag that is a simple difference method of showing when we started having dropouts of that feed rate. And what we found is the 16 centimeter marker has max range of 10 meters, minimum range of 0.6. And then the 1 meter marker got us all the way out to about 37 meters before we started having dropouts. Now, this is not necessarily what was expected. I personally expected that as we scaled by a factor of like 6.25 up, we were going to get an associated scaling, so 62.5 meters expected max range. But in my infinite wisdom, I did not print a big enough white border around to do that line detection, which is critical for the Aruco method. And so that large marker that doesn't have the white border is likely getting confused with the desk it was propped up on. And so that is a potential area of improvement that we need to evaluate. But this laid a framework for like the size selection that we want to have and what ranges we can operate at when coming into land on the boat. Next, like I discussed, we implemented this 1/10 scale model yard patrol craft in the motion capture lab at Naval, and had markers on the boat and on the drone. And then we had an array of the Arucos all over. So what we saw also during the initial trade study is that Arucos are very susceptible to occlusion. So if you can't see the entire marker, you will not get any kind of estimate. So we implemented an array of various sizes all over the boat to be able to make sure we get an estimation all around. And then we marked those up and then also had bounding boxes drawn around to also test, do neural network testing in the future. And so this is what it looked like when we break down the motion capture data. We've collected 1,007 data points of the drone flying around the YP and tying in the image data with the motion capture data. And this is what the motion capture data looks like. That red track is the drone flying around the target. The blue arrows are the orientation of the camera. And that blue square is the landing zone that you see back there. So this is our ground truth. And when we relay it, those black dots are the computer vision's pose estimation in the X, Y, and Z translation. And what we immediately observed is it's likely we're getting more or less expected that as the range, as we get further out from these relatively small markers, they range from 3 centimeter to 9 centimeter in size on the YP. There's increased error when you're further away. And so when we looked at the range testing, we see that between the ranges of 1 to 5.5 meters, which is the furthest we could get out, we have an increasing error up to about 20% of like what your range is. This is like pretty concerning, like when you immediately look at it, that we're getting this kind of variability. And I believe it has to do with the fact that that array of Arucos is not accounting for if there's some like crazy outlier from like a high aspect angle. So what I mean by that is, let's say instead of viewing a marker, one of the markers head on, you view it at a pretty like steep, like almost side on angle where you can't see the whole thing. You're gonna get some crazy value that gets pooled in and is producing outliers as we get further away. Or simply, as discussed earlier, you just can't, we don't have proper white bordering to get that line detection. So we need to work to understand what is the optimal array. And considering how small the markers are, that could also be a factor. We should do flights on the YP collecting data to see what our performance in the actual maritime situation looks like. But the promising thing is that as we hone in and we have this, as a drone comes in to land on the boat, it evidently needs to be more and more precise in its lateral movements in order to, not hit the ship. But as you're further out, you get more leeway into where it can deviate. And we need to determine, something we need to establish is what are those exact performance specifications? What are those limitations? Like how are we gonna certify that something is precise enough to come in and land on the ship? So looking at potentially implementing some fusion between the inertial measurement unit and the flight controller and what the computer vision system can observe to get increased precision is another potential avenue, and refining our Aruco array. Getting into the neural network testing, so shown here are two different YP classes. So on the left you have 676, which is a wood hull. On the right you have the 703, which is a metal hull. Some minute differences. And a third class that we considered a third class is the 689, which has the flight deck on the back of the wood hull. And what we were interested in is, just as a foundational experiment to determine the viability of using neural networks, is can we differentiate between the three classes at different viewing angles? So, and also serving as a dress rehearsal for safety procedures for that integrated flight test. So we went out on the Dewey Seawall, filed our flight plan with the USNA airspace, and we conducted 10-hour to 2-hour drone flights where we had a YP with Commander Costello on board, cruising around, taking pictures, video for our neural network training, and experimenting and running through the different safety procedures, like ensuring that we had proper communications between onboard the ship and the safety observers on land, and how that would work once we get to the flight test. But of course, we're going to run into issues. And I've had the police call on me 3 or 4 times throughout the academic year. Someone running by sees no drone zone, and then all of a sudden the cops come out guns blazing. So that was an interesting experience. But again, it's all part of the process of learning to operate within the USNA airspace. I'm sorry that it's difficult to read. I'm realizing this now is probably not the best graphic, but what we essentially, from the classification problem, what we need to understand from the neural network that we model that we implemented. So we have 1,970 images that came out of the test days, and we labeled the different YPs at different aspects and different lighting conditions, trained it over approximately 300 epochs, and then we evaluated over approximately 430 images. And what we found is that YP676 and 689, when you don't have a rear aspect view, are just getting confused, which is expected. But we need to find ways that we can ensure that when we're doing the flight test and using the neural network to hone in on the ship, we're landing on the right boat, because that would not be a good day if we honed in on a fishing vessel. And additionally, at ranges greater than 400 meters, the You Only Look Once model, which is the openly available convolutional neural network that we use, has difficulty with those small objects. So we probably are going to, if we want to extend our range greater than 400 meters, we're going to need to use a prime telephoto lens, fixed focal length, and transition between sensors, which is, again, a system integration problem. This is where I spent 85% of, most of my time. I use the analogy that it's like getting a ballroom of dancers that don't speak the same language, and the music is not right for any of them to talk to each other, work together, and get in synchrony. We have the computer vision system that needs to talk to the flight controller and get everything working and talking together in harmony. And I have many, many, many scripts on my computer of this not working and documentation of why it didn't work and why we're trying to work to get everything integrated together. But what we have gotten is the two systems working separately. So as we showed you, we're getting computer vision estimates. And also, I've got the companion computer to run a pre-scripted autonomous flight where it's essentially emulating ground control station commands and going from a GPS waypoint to another and landing autonomously. We need to bring the two together to get to that TRL6 that I talked about in the beginning and actually get up and running with this integrated flight testing plan. How do you eat an elephant? One bite at a time. When I got on board with this project, it seemed like a mountain of, I was really excited because I was taking my childhood passion of model aviation and getting to work on it in a research sense, but it seemed like a mountain. And being able to divide that work into sizable chunks is some part of the project management endeavor that has been a terrific learning opportunity through failing. Additionally, NDA compliance throws a huge wrench in the process of being able to test and get the system up and running. As stated before, GW, it has PhD researchers that have their own system, and we've gone to them for guidance, but their hardware is not compliant with the National Defense Authorization Act. Basically, our stuff can't be made in China, and a lot of the stuff is, made there, so it becomes an issue. And then for nearly a month and a half, in the middle of our academic year, we experienced a flight freeze. So no drone operations were authorized on the yard, which additionally threw problems in our testing. And if we were up and running for integrated flight test, that is something we have to learn how to accommodate and get around. Additionally, purchasing. We had to purchase all our equipment, our requisite equipment, back in July. And that was a challenge to know exactly what problems we're going to have, what hardware we were going to need before getting into the lab testing and everything that we had gone into. So this is the reality of engineering research and how we need to plan accordingly. Good thing though is that we believe that although we're getting some higher than desirable error in our Aruco array on the YP, it's showing, I would say it is a viable solution of repurposing existing techniques and hardware for our emergent application for defense. And then we laid the foundation in the procedures for doing an AI integration where, again, neural network visual servoing the drone to hone in on the YP at further ranges and then closing in using those Aruco tags. And then lots of documentation on how not to do this. Yeah, that was a very foundational learning experience is you try again, and documenting how it didn't work so that future researchers don't make the same mistakes. I want to personally thank Commander Costello, Captain Newarner, the Trident Committee, and Professor Schroeder. It's been an incredible learning opportunity to continue my boyhood hobby into this research capacity. And yeah, thank you so much. And I'd like to open it up for questions. Sir.
Thanks, Adrian, for a nice talk. I wanted to give some feedback about the process of trying something and it not working out perfectly. I think that's just part of the standard engineering experience, part of the scientific experience, and the Trident scholars that are there and future Trident scholars, I think it's important to realize that that every engineering project that you're doing is part of a continuum. So you've done a lot of the work that will be built on by others. I think it's maybe a little too strong to speak about it in the ways that you did as if it was a failure. I think it's really just incremental progress, and you've made significant progress at the outset of your project. So I really appreciate the work that you've done, and especially under the constraints that you identified. I think that will help other Trident scholars that are going forward with their work. So well done.
Thank you, sir. I really appreciate it. Professor Knight.
So I'm just wondering, you mentioned briefly about maybe using a telescope or along the focal-length lens. Could you talk more what the future might be if you had, say, more weight constraint or fewer weight constraints, I guess, or cost constraints?
Yeah. So what I envision in the near future is, like you mentioned, implementing different optical sensors that can view way further out, and so we can see how far we can extend the range to conduct these terminal launch and recovery operations and test and evaluating their performance. But way out, this is limited. This research is limited to the terminal environment, but it doesn't address how you do the transit problem where you don't have GPS or radio communications. And we've been actually approached by the Stevens Institute to implement CELNAV, celestial navigation, small celestial navigation modules on our drones that can see the stars even during the daytime and use that to navigate over long distances, which is optimal for, say, navigating over water where you can't necessarily look down using a camera and geo-reference your position. So that's, again, given our current technology readiness levels, that's a way out problem, but it makes me really excited to see that kind of system integration and what we can do to restore operational effectiveness to the fleet. Thank you, sir. Professor?
Thank you, Adrian. Lots of problems dear to my heart, meaning nothing works. What I'm asking you, I'm asking you a very difficult question, and that is now you're one year or more mature in this project. How could you scope it to be realistic? Because obviously you were fighting far more than you could chew. So now, with all of that experience that you have gained, can you sketch in 2 sentences what project is realistic in scope to be done
I would say that it would have been more realistic to hone in on those pose estimation methods and just looking at either just the fiducial performance and how we can improve it, or just the neural network performance and how we can improve that, instead of trying to do that plus the system integration task. Or just one of those three things that I tried to address to get us going, I think could have been investigated more in depth and have a greater understanding of, and made a ton of progress in that area instead of incremental progress in all three. Yep, it did. Thank you, Professor. Any other questions? Sam.
Are there any Tridents or capstones next year that's going to continue your research?
Say again?
Are there any Tridents or capstones next year that are going to continue?
Yeah, we were currently working a turnover with a guy who's we've baited to take over this project. No. It's we're very excited for getting a WRC, like an actual roboticist, to come in and work on this project. Yeah.
Let's thank our speaker one last time. Our next speaker is Midshipman Sebastian Martin. He's from the 20th Company from St. Louis, Missouri. His service assignment is explosive ordnance disposal, and he'll be going to the Naval Diving and Salvage Training Center in Panama City Beach, Florida.
Yep.
Okay.
Awesome. All right. So my project is entitled Allocation of Surveillance and Search Assets in Undersea Warfare. My name is Sebastian Martin. My advisors, Anna Seversko, Daphne Skipper in the back. Also would like to give a thanks to my friends who are here, and my beautiful fiance and wife-to-be, Elizabeth. All right, so starting off this project. So what is the problem that we're solving? So let's picture an image like we have on the left, which is the open ocean with traffic routes that are between certain areas, and we're going to try and place sensors. And so we're going to look at a similar image on the right, which is a smaller grid cell version of this image of the Bering Sea. And so each of the numbers are going to be the traffic intensity or the amount of ships that are traversing that cell at a certain time period. And we want to figure out where can we place sensors, and these sensors have different ranges, these sensors have different detection capabilities, and how can we optimally place these sensors, because they are independent sensors and they're going to have overlapping probabilities of detection. And so how can we optimally place these sensors to detect the highest expected value of the submarines? All right, so the overall goal, like I said, is the optimal placement of sensors, maximize the expected value of the detected target submarines, and we're going to depend on a few different things like traffic intensity. Each cell has a specific value based on where it's located, and then also the probability that the submarine's actually in that cell. So moving forward, what does this mean in math? This is the model. We'll walk through it because I know it may not make a lot of sense in its current form right here. So first, the model objective. This is my overall goal in math format. So like I said, those historical traffic intensity, the iota values, are going to be how many ships have traversed through that cell in some historical period. And so this map that I'm using is just a merchant shipping map because most of the submarine data is actually classified. And so this is a merchant shipping map, like I said, in the Bering Sea. And it has that cell right there. It has 5 ships that traversed it in a certain period of time. And so we're going to use 5 as the iota value. And then the probability of detection value. And so we're going to look at this cell in the bottom right corner, and you see that it has 2 sensors that are covering it. And so the probability of detection is actually a combination of the independent probability values, and we're going to go through how we calculate that, but that's going to be what goes into the new value. So this is our first constraint, and what this constraint means, all it means is that a sensor can only be placed in one cell, which makes sense. And the second constraint here, this is the more complex one. And so this new value, like I talked about, is the probability of detection for the cell we're interested in. So it's not the probability of detection for the cell that we place a sensor in. It's just a random cell in the ocean. We're trying to figure out the probability of detection for that cell. And then we're going to do this constraint for all of the sensors of all the different types that are in range of that cell. So if there's multiple sensors that cover the cell that we're interested in, we're going to apply this constraint over all of those sensors, and it's going to find our probability of detection. So now we're going to explore what this means, which is our more complicated constraint. So like I said, the ij values that we're going to see are the probability of detection for the cell we are interested in. And then the I prime, j prime are the cell location in which the sensor is placed in. So we're going to need to keep those straight because it kind of gets a little confusing. So let's picture this scenario here. We have the cell that's in red is going to be the cell that we're interested in, and it has 2 sensors that are overlapping. The green sensor is actually not placed in that cell, and it can cover a 3-cell area in either direction. And then the blue cell, or the blue sensor, covers 1 cell, and it's placed in that cell that we're interested in. And so this first alpha value, this is going to be the degradation of sensitivity. And essentially what this means is just the percent of detection capability that's remaining as you go further away from the cell that the sensor is actually placed in. And so you find it by the placement of the sensor minus the placement of the cell that we're interested in. And it's going to be essentially a percent that's left of our detection capability. And so that's this value for blue because it's placed in the same cell, so it's 0 away. And then for green, since it's placed 1 cell away, we're going to have 1/4 of the detection capability left that we would have if the green sensor was placed in the same cell as the cell we're interested in. And then this delta value is going to be the probability of detection. So each sensor has a different probability of detection just based on what type of sensor it is and the sensor capabilities. And so these are going to be the delta values there for the blue and the green. And then this mu value is essentially just whether or not the water is clean or dirty. And this depends on a lot of different factors. It depends on water depth. It depends on where it is in the ocean. It depends on if there's weather that's stirring up the bottom. And there's going to be different classifications of water. And for this example, we just classify clean water as 1, dirty water as 0.5, and both of these cells are going to be clean. But when you start to look at waters that are around different islands in the ocean or waters that are affected by a hurricane, they're going to become dirty water. So we need a placement holder to account for that when we're talking about detection probabilities. So we're going to walk through some of this math. So for the blue sensor, like I said, we've got the 1, we've got 0.3, and we've got 1, and there's 1. Our decision variable, the omega, is by type of sensor. So we have 1 type of blue sensor that's in range of the cell, so that exponent is going to be 1. And we take 1 minus that to find the probability of not detecting, because like I said, these are independent sensors. And so we want to find the probability of not detecting of each different type of sensor, and then we're going to mix those together like we'll see here. And so the green, same thing, using the green values. And then so the probability of not detecting is we multiply both of our non-detection probabilities together. We get the probability that we're not detecting, and then we're going to take 1 minus that to get the probability of detecting. So for the cell that we indicated, the probability of detection by our 2 sensors is going to be 0.3875. So we're going to do this for every cell that we're interested in, which is every cell that could be covered. But that's just an example for one so that we could walk through this complicated constraint. However, this is nonlinear because we do have that decision variable in the exponent. And so this is non-convex and nonlinear, which makes it incredibly hard to solve. And so we're going to need to somehow transform this constraint into something that's a little bit more solvable. So then we come to the nonlinear convex model, which we apply a linear transformation, a logarithmic transformation to, and we get something like this. The exponent comes down in front of it. And so we're going to take this, which is after applying the logarithmic transformation, and we're going to declare that a new variable, which is called psi. And so that's a new decision variable that we've now introduced. And we're going to set that as a constraint in our model. So now we've added an additional constraint and an additional decision variable. And our model is going to look something like this. So this is the nonlinear convex model, which is a solvable model. And we've applied that logarithmic transformation, and we've added a new decision variable. However, this is still nonlinear because we added a new decision variable, and then the decision variable was also in the exponent. And so now we need to figure out how we can transform this into something like a linear model or a linear approximation, which is what we're going to use, which is going to replace this nonlinear model. So this red line here is our nonlinear constraint. Like I said, 1 minus e to the psi. And we're going to approximate it using tangent lines. And an example tangent line is something like this blue line here. And essentially what you want to picture is how close do these tangent lines have to be in order to stay below some error tolerance. So we have three tangent lines in this picture. The green is an asymptote, so that's not a tangent line. But these other 3 lines are are tangent lines. And so these tangent lines essentially replace the red line in our approximate linear model. And so what is the error? This is an example of the error. What does the error between these things need to be so we stay below some error tolerance so that our model is still accurate even though it's an approximate linear model? So what we found and what we proved in our paper is that the maximum error occurs at the tangent line that goes through the origin and with a large W value. The W value is going to be the width between our tangent lines, essentially how close to our tangent lines have to be in order to stay below some error tolerance, which is this. And the error tolerance, we're going to set a conservative value for our project, which is just 10% of our minimum probability. However, you could set it to be whatever you want to be. But since this error occurs at every cell that's covered, we need to divide by our total number of covered cells so that the total probability error is within our error tolerance, which is 10% of the minimum probability. So we solve for this. And then this is our maximum error between our tangent lines. Like I said, the maximum error occurs at beta equal to 0, which is the tangent line through the origin. And so we set this equation, we get our error tolerance that we're willing to tolerate, and we solve for W value, which is our width between our tangent lines. And then that will tell us how many tangent lines we need because we build our tangent lines from 0 to from our minimum probability, and then minimum probability minus W all the way up to our maximum probability. So with our results, this is the model that we solved over, or this is the data that we solved over. This is the picture that you saw in the beginning. And then these are the values of the different sensors that we use. So we use 3 different sensors, and they can each detect a different range, and they each have different detection capabilities. And this is where our model places the sensors. And it may seem a little bit obvious, so you would place them along the track of where people have been traversing. However, with the overlapping probabilities, it'd be impossible to find the actual optimal value of this without using some sort of mathematical modeling like I've displayed here. And so our error analysis, this is important because we can compare the linear approximation model with the nonlinear model. And so the nonlinear convex model we solve using ample, nonlinear solver, ample and barren. And then the linear approximation model we solve using Gurobi. And these are some statistics to compare the two. So the objective values quite close. The total probability value also quite close. And then you can see the size of the linear approximation is much bigger, just mostly because we have 343 tangent lines. And so those add different constraints. But the solve time is still faster. And so when we start to expand this model, it's important to note that the solve time for the linear approximation is actually faster than the nonlinear model. And so it's useful if we can stay below our error tolerance, which you see we have. 10% of our minimum probability is 0.003, and our total probability error is 0.0004. So we've stayed within our error tolerance. And so this model is highly accurate to the nonlinear model, and it solves faster. It provides a little bit ease of solving. So now we have a detection, we've optimally placed these sensors, and we have a detection. And that detection may look something like this. So this is actually 2 detections, 2 different areas of uncertainty, like we're going to call them. And these detections, we need to respond to them fast because ultimately they go something like this. This is 10 time periods later, and now it looks something like this. And the shaded cells are the probability of where that enemy submarine could have gone. And so we've placed our sensors, we've got a detection, and ultimately that gets us nothing unless we can respond, unless we can go out and we can find and we can track that enemy submarine. And so our second part of this project is a tactical search model, which assumes that we have a detection, and it assumes that the AOU is expanding as time period goes on. And so we want to optimally dispatch our searchers, our different assets, which all have different capabilities, to go out and find that detection with the highest probability of the expected value. So what does this look like? So we have our input, which I said are AOUs, and then our search model, which are a series of logistical constraints which limit the capabilities of the searcher based on their actual capabilities. And then output, it's essentially going to tell each of our searchers where exactly to go and where to search in a certain time, in a certain time period. And then the overall goal, like I said, optimal routing of the search assets upon detection to most efficiently utilize naval resources in tracking and neutralizing enemy submarines. And so we assume that once our searchers get to a specific cell, they employ already existing search methods like you see on the left. However, we are going to route them to which grid cell location to go to, because these grid cells that we optimize or that we solve over are 5 miles by 5 miles large. So you essentially can't just do this for the whole ocean. You need to know where you're going, and then we're going to employ one of the existing search methods that have already been highly researched. So some considerations, like I said, searchers are staged at base locations. So we assume that a searcher can't just magically appear somewhere. We need to start from one of our base stations, whether it be a carrier strike group, whether it be a land base station. We need to go out and we need to go to the detection. And then searcher types have different endurance and downtime limitations. So our searchers can only stay out for a certain amount of time before they've got to go back and fuel, man, all that stuff, have liberty, morale, and all that good stuff that we need. And so searcher types move at different speeds. You can imagine that a helicopter would move much quicker than a DDG, and so we account for that. And then they also have different detection capabilities. Some searchers are better at detecting submarines than others. And then we also have limited resources. So our search model objective, again, our goal in words. So this p-value is going to be the probability that the target is in a specific cell at a specific time. The O value is going to be the probability that the searcher can actually detect that target. And then the value, we allow our model to place a higher value on a specific enemy based on what we may believe it to be, or what kind of strategic importance that enemy may have on the homeland. For example, if an enemy is closer, we can assign a higher value so that the model inherently tries to search for that enemy more than the other ones. And then our Y decision variable here places our searcher in a cell at a specific time. And we're trying to solve this to maximize the expected value of targets across all time periods, cells, and searchers. So some of our constraints, these aren't all of them, but we're going to walk through a few of them here, maybe more than a few, and we're going to see what they do for our model. So this is essentially just saying that our searcher has to be searching or has to be in a no-search state. We'll get what a no-search state means in a second, but that's important. It's essentially just saying our searcher's got to be somewhere and doing something. And then only so many searchers of a specific type allowed in a cell at a time. That should make sense. We don't want to have, we limit our model into placing 10 surface ships in the same cell, right? Because they can't actually operate that closely together when they're searching for something. So that's just a placement holder, and we don't know what those values actually are. But for this model, we limit only one searcher of a specific type can be in a cell at one time. So we can have a surface ship, a submarine, and a helicopter searching a cell at the same time, but we can't have 3 helicopters trying to fly in a 5 mile by 5 mile area. It probably just isn't, that doesn't work. And then this one, like I said, the no search variable. So we allow our searchers to go into a no search state, which essentially just means that you're transiting or that you're down. So transiting means that I'm going to turn off my searching capabilities, and I'm just going to get there as quick as possible. I'm going to turn on the jets. I'm going to go full speed ahead, and I'm going to try and get to a certain AOU, and I'm not searching, but I'm also not down during that time. I'm burning fuel. I'm using up time. And so our down variable, that indicates that we're down. That indicates that we're back at the base station, or we're refueling, we're stopping, we're doing anything except for searching. So we're going to turn on that y prime variable. And then these constraints, we essentially just need to know when a searcher starts a search, and we need to keep the searcher in that cell for a specific amount of time so that they can complete the search. And that's what these three things are saying. And they need to just stay in the cell to complete the search once they start the search. All right, and this one just says that we need to start at our base stations. So it should make sense that we've got a dispatch from our base stations, and this is enforcing that. And then after our endurance time, which is that uptime, elapses, we need to return to our base station, and we need to go down. And so say we've been up for 5 time periods and our endurance time is 6. On the next one, we need to go down, and we need to go down back to a base station. So it's going to take that last time period off, and it's probably going to transit to the base station, and it's going to go down at one of our base stations. And we assume that our searchers can go to any base station and go down. We don't limit them to go back to the one that they dispatched from. However, that is a consideration which we could take into account in the future, is we don't really know if, when a helicopter's out searching, if it's going to go back to the ship that it came from, or if it's just going to go to any ship and get fuel and then go back out. And then this one, it's just saying that once we've gone down, we need to stay down for a certain amount of time to refuel, go on liberty, and do all the stuff that we need to do. And then this is essentially just enforcing that if we're transiting, we can go further than if we're just searching. In searching, we can go to the adjacent cells around it, and in transiting, we can go much further. And this is limiting the movement to that. And so this is our notional scenario and results. This is the data that we solve over. So like I said, the base stations are indicated by H's, and then we solve this one over 100 nautical miles by 100 nautical miles, and we solve it over the 10 time period results, assuming that we get there at the 10th time period. And this is what our AOUs look like. Again, the shaded values are just the probability values of where that enemy submarine could have gone. And these are the searchers that we use. We have a surface ship, a helicopter, and a submarine, each with different capabilities. The endurance time for the submarine is infinite. We assume that they can stay out forever. Likewise, downtime doesn't apply to them. The other ones, we assume that the helicopter can travel much quicker than our other searchers, which is indicated there. And then we just assign placeholder observation probabilities based on the actual data, which is classified and we can't use. So these just allow your model to hold that value so that when we do turn it over to the Undersea Warfighting Development Center, they can plug in the real values and still solve this model in its current form. So these are surface ship results. So it's going to start at the base station. It's going to search these cells, going to go back to the base station, fuel, search these cells, again go back to the base station, and then it's going to keep searching. And these are the cells that it searches over. This is just for 20 time periods. So you can imagine that it would go much longer than that as well. But this is just 20 time periods, and we assume that they need to stay in the cell for 2 time periods, which is why we only have 7 cells that are searched, because we have to have some downtime and we have to stay there for 2 time periods. The helicopter, it moves much quicker, so you'll see it cover a larger area. So we start at the lower base station in this one. We're going to search a few time periods down here, and then we're going to transit to the upper area of uncertainty, and we're going to search a lot there. And we're going to have to go back every 3 time periods and refuel. And these are the areas that this one searches. So you can see that the helicopter covers a much larger area than the surface ship. And the submarine, it's really boring. It's just going to search 4 cells super slowly because it's a submarine. And it looks something like that. And so our contributions this semester, like I said, we developed a strategic model which determines the placement of the sensors. And in its direct form, it's nonlinear. So we linearize it through an approximate linear model, and we allow the user to provide an error tolerance that they're willing to solve for. And that determines the size of the model, the number of tangent lines we need, which also affects solve time, stuff like that. And so we approximate our nonlinear model. And then the tactical model, it determines the routing upon a detection and incorporates logistical requirements such as allowing searchers to transit to non-contiguous search areas and restricting the length of searcher uptime and downtime requirements, which are really just logistical requirements of any searcher and any tactical asset that we have. And then we test each of the scenarios in a notional scenario, but it's pretty accurate, and we developed it to be pretty accurate. So we could use data that is classified, or they could use data that is classified on the same model when we turn it over to them. But for now, we just plug in placeholder values, and we solve it over a problem that looks pretty similar. So does anyone have any questions? How's it going, sir?
Hey, Sebastian, good presentation. You're modeling as ships, aircraft, and submarines. I'm wondering, having flown helicopters off of ships, did you account for mobile base stations? Meaning, if you move a ship in your scenario, that's then a different base station for a helicopter.
Right. And so we did account for it. Unfortunately, when we implemented it, it grew the size of our model significantly. And so in this model that we solve using like the equipment and the computer that we have, we chose to have stationary base stations, and we had solved for 1 hour of time, which is the 20 time periods. However, it is a consideration, and it is logistically accurate that you would have helicopters on the back of a DDG, which is also moving, and so that base station is moving. And so in the future, we would hope that we could limit the size of the model in terms of constraints so that it could solve faster when we did implement that. How's it going, ma'am?
You did a great job, Sebastian. So I have a question for you. Did you look at the robustness of your initial placements in terms of the quality of the data that you fed it to determine where the sensors should be? Like, if you have a sense of how much error in that data, what that results in terms of sensor placement?
Yeah, so when we solve the nonlinear model, which is the model that has the exponent of the variable, we get an objective value and a solution that's slightly different than our linear approximation model. And so there is like a little bit of error there, but essentially what it was doing were the two models were placing just different sensors in mostly the same cells. And so it has very close, very close probabilities of detection, that total probability of detection. And so the error is quite small. And we did solve this problem by hand and see that it does place the sensors mostly where you would expect them to be placed. How's it going, sir?
Hi, Sebastian. I'm Commander Ryan Yoder from the History Department. My last tour in the real Navy before coming here was at UWDC, actually, so I'm really interested in this. I have a question and a suggestion. So you mentioned your multiple base stations and the assumption that any unit can use any base station. Are there different base station types based on the type of searcher, or is it all just a uniform type?
So right now there's not. The base stations are all the same, and we assume that any searcher can go to any base station when it needs to go down. And we just start them from specific base stations, but they don't even necessarily end at that same base station. And so that is something to assume in the future. Where the tactical model is going to go is we're going to solve it over a shorter time period, and then we're going to update the probability values so that the probability of a cell that we already searched would be lower. And then we're going to run it over a simulation, which would essentially give a larger time period of results. And in that one, we could add constraints because we're solving it over a shorter time period, and the model would solve faster. So we could add constraints like that and like the moving base station and a few other constraints. Because right now, when we solve it just straight like this, it's a very large model, and it does take a significant amount of time to solve. And so we were really trying to balance, the solvability and the solve time with the actual logistical requirements that are there.
So that actually may connect with my suggestion. This may be technically infeasible, but what I would say is that if you can make it so that you are able to manipulate whether unit searchers can use different base stations or whether they have to go back to their original base station, there is some doctrinal answer to that. Like the way the fleet works is, for example, if you're a helicopter that takes off from this ship, you have to go back to the ship where you went. I don't know what the answer to that is, but there's an answer. And if you make that manipulable, you could compare the degradation in search effectiveness by requiring searchers to go back to their own base station versus what the effectiveness would be if they're able to go refuel on any other ship, for example.
Right.
That would be a really useful piece of information to see that comparison.
Yeah, for sure. And like I said, we've been working with UWDC this semester, and they've been providing us like limited feedback essentially. And this model has been like turned over to them, and it's still going revisions. We have a grad school student who's going to be taking it from here and working on the revisions with them as well. And so I hope that they can take it further than I could just in the one semester that I worked on that independent problem, and definitely incorporate some of those fleet logistics. How's it going, ma'am?
Hi. Really enjoyed your talk. I flew P8s, so we do a lot of sensor placement and that kind of stuff when we work. I was curious when you were talking about your probability of detection, did you consider at all whether or not a submarine was either alerted or unalerted by the presence of a sensor and how that might affect the model?
We didn't, and that is important, the counter detection capability that those submarines have. And so we essentially were looking at, in the surveillance placement model, in the sensor placement model, we were essentially just looking at, say we have a log of where we've detected submarines in the past, like we know kind of what routes they use and what routes they like to use in the ocean, and we're gonna place long-term sensors there, like moored sensors, so that we can maximally find the number of detected submarines. And so, however, if they know that a sensor is placed there, then they're just going to change the route, and it's going to mess up the whole calculation. And so that is something that we should take into account, because likewise, when I presented the tactical model at our Informs conference, someone asked, well, wouldn't they change which way they're going or the way the area of uncertainty is expanding if they know that you're also searching for them? And that's also a very good consideration and something that could be worked on in like the simulation part. But for now, we don't, although I do think it would be a good idea to incorporate that. Sam?
Hey, Sebastian, you had that like linear approximation technique
Mm-hmm.
To find epsilon and all that. Could that be applied to any nonlinear non-convex constraint, or is it more specific to your model?
No, yeah, it can be applied to any nonlinear non-convex constraint mostly, I think. I don't know, this was my also first time like taking a nonlinear model and trying to linearize it, and it was a good experience, and it was cool to like try and solve like below that error tolerance. And also, like what I was talking to my professors about is this model could be used to just generalize to like any historical traffic intensity problem that you have where you're trying to like place people in there to find them or to intersect them. But I think that it can be used to most nonlinear non-convex constraints.
Let's thank our speaker one last time.
Sweet. Good luck.
joining us. If you are around for the afternoon, our session will also continue in the afternoon, so please stop by if you have a chance. Our next speaker is Midshipman Andrew Colazar. He's from the 22nd Company from Haverstraw, New York. His service assignment is submarine warfare. But in the fall, he'll be attending Wake Forest University to pursue a master's degree in mathematics.
Thank you, Dr. Schroeder. So like Dr. Schroeder said, my name is Andrew Colazar, and I'm here today to talk to you about geometry of numbers over real quadratic number fields and its applications to quadratic forms. And now I know this title seems like quite the mouthful, but we'll start with just a brief overview and some definitions to get started before we start actually getting into the math. We'll try to ease into the more digestible stuff before we get into the very technical portion. So to begin, this essentially is a project in number theory, which is the study of the integers and more specifically the prime numbers. We take a look at how they interact and the properties of them and how we can use them for broader mathematics. Specifically, we are trying to understand which integers are the outputs of relatively simple functions. This serves as the foundation for modern cryptography, and all modern crypto systems use this technique. If you look at like Diffie-Hellman, relies on exponential functions. Elliptic curve cryptography focuses on a type of function called elliptic curves. But for our specific purposes, we are looking at a type of function called a quadratic form. But what is a quadratic form? Well, it's a function where every term possesses exactly two variables. So in order to try and demonstrate this, can anyone tell me, is this a quadratic form? Yes, it is. What about this one? Yes, it is. And lastly, no, it's not because of that 3x term. Very good. Now that we have that out of the way, I mentioned that we're looking for the outputs of these forms. When we're looking at quadratic forms, we say that an integer is represented by the quadratic form if and only if it's one of the outputs. And so when we're trying to look at this, we take the following quadratic form, x squared plus y squared plus 3z squared. Can anyone tell me is 5 represented? Well, it is. If we plug in 1, 1, 1. What about 6? Same equation. It is actually not. And so it is important to know that what we are trying to do is it's important to know that any quadratic form that represents all non-negative integers is called universal. A natural follow-up question to this would be, well, what, if any, quadratic forms are universal? And if they exist, how many are there? This has been a long-standing question in number theory that dates all the way back to the 1700s with the work of Joseph Louis Lagrange. More famously known for Lagrangian multipliers or Lagrangians in physics, he did also dabble in number theory, and in 1770 proved that the sum of 4 squares is a universal quadratic form. In addition to this, he also proved that the minimum number of variables needed to be universal is 4. But if we take any integer, so let's say 4, and we wanted to write it as the sum of 4 squares, we can do that. One possible solution would be if we plug in -2, 0, 0, 0. This is not a unique solution. We can plug in 1, 1, 1, 1, and there are others as well. Much more recently, in 2005, Bhargava and Hankey attempted to further this problem by announcing their 290 theorem, which states that any quadratic form that represents all integers from 1 to 290 is universal. They also claim that there exists 6,436 universal forms in 4 variables. This had such a profound impact that when Bhargava was awarded the Fields Medal in 2014, the 290 theorem was cited as one of his major contributions to the mathematical community. However, once Bhargava was awarded the Fields Medal and Hankey was denied tenure, the 290 theorem never formally appeared in print. So since they left for very, very different reasons, we cannot assume the 290 theorem or its proof to be true. And we do know, however, that they relied on much more analytical techniques involving the theta series and modular forms, and we decided to look at the problem from a more classical approach in a field of math called the geometry of numbers. Doing this, the ultimate goal of our project was to take a look at a list of quadratic forms and provide the first formal proof that these forms are universal. When we began this program, we decided that it would be best to look for ternary or three-variable subforms whose representation is known and has been proven using GON-based techniques by teams of undergraduates to include a former Navy grad, class of 22, Ensign Rainier, and use these to prove that the larger four-variable forms are universal. To demonstrate how we did this, consider the following form. We've been able to prove this is universal by setting y equal to 0, and we get one of our GON-based ternary forms. This one in particular represents all integers that are not of the form 4 to the k times 16l plus 2. It is important to note that when we're looking at these, since these equations are quadratic in nature, we know that if all square-free integers are represented, then all integers are represented. And so we only need to consider when m is square-free. So in particular, we're looking at when m is 16l plus 2, meaning it is not represented by r. For those of you more familiar with modular arithmetic, we're looking at the case where m is 2 mod 16. And so we see here highlighted in orange are the terms that go away when we set y equal to 0. And when we do this, we know that m is not represented. So if we're trying to show it is, we needed to make sure that our y value is non-zero. So let's try the simplest non-zero integer we can think of, 1. Well, when we plug that in and set the rest of our variables equal to 0, we see that 2 is represented. Well, that's our first case done. Only infinitely many more to go. So to try to speed this up, let's try a different value for y. This time, let's set y equal to 2. And have all of our other variables be some non-zero for this case. And we can expand this out. And a common technique that we're going to do throughout this is we're going to try to limit the amount of cross terms that we have. And so we're going to complete the square, hence why we chose an even value for y. And when we complete the square, we see that we get the following. What we can do is we want to show that this equals our integer m. And so in order to show this, what we're going to do is we're going to move our constants over to one side. And we see that we get the GON-based ternary earlier equal to m minus 7, evaluated at x plus 1 z and w. And so if we can show that this x plus 1 z and w exists and represent m minus 7, then we're done. In order to do that, we must first show that m minus 7 is a non-negative integer that is not of the form 16l plus 2. It is important to note that since we've already covered the case where m equals 2, we can look for when it's strictly greater than that, meaning our minimum choice for m is going to be 18, and so we know it's non-negative. That part's good to go. We are more interested in the 16l plus 2. Well, m minus 7 is going to be equal to 16l minus 5, and so we're good. If we look at it from the lens of modular arithmetic, this means that we're looking m is going to be 11 mod 16, so clearly not 2 mod 16. So we're done. So since m minus 7 is represented, so is m, meaning all non-negative square-free integers are represented by our quaternary form q, meaning it is universal. This proved to be quite the fruitful technique, and we were able to use this to prove 66 different quadratic forms are universal. However, there were many, 22 of them, who possessed a GON-based ternary subform that this technique was insufficient in providing a full formal proof of universality. It gave us only a partial solution, and we needed to start looking at it through a different lens in order to expand it into a more full formal solution. In order to do this, we had to shift into the realm of point set topology, and specifically looking at regularity. And so regularity is a property of these forms, and we say that a form is regular if it represents an integer under mod n for all natural numbers n, implies that it will represent this integer over the integers. And now, this gives us infinitely many computations to do, so we're going to have to simplify this a little bit. Fortunately for us, in 1996, Jaegi and Komplowski proved that there exists 913 regular ternary forms that we can work with. However, unlike our GON-based ternary forms, they did not list the representation of these. And so if we want to use these for our advantage, we must first prove that the integers we're interested in are represented. In order to cut down on our number of computations, we can first use the Chinese remainder theorem, which allows us to, instead, rather than looking under mod n for all natural numbers n, we simply have to work under mod p to the k for all prime numbers p and all natural numbers k. We can simplify this further using a tool called Hensel's lemma, which allows us to find a specific natural number t, such that if we can find our solution under mod p to the t for that t, this will escalate to all higher powers of that prime p. This will lead us with finitely many computations to make and makes our problem actually solvable. So to demonstrate this, blame my last. So in order to use Hensel's lemma, we must first develop the notion of a p-adic norm. And the p-adic norm is just defined as the highest power of a prime that divides that integer. I know this seems a little confusing, but to demonstrate this, we're going to look at when the integer is 6 and the prime that we're looking at is 2. If we are trying to demonstrate the 2-adic norm of 6, we see that it is 1/2 because 2 divides 6. 6 over 2 is 3, but 2 squared does not because 6 over 2 squared is 3/2. When using Hensel's lemma, if we can show that the p-adic norm of the quadratic form minus m is strictly less than the square of the p-adic norm of the gradient of that same equation, then we know that our integer is represented. See how this works? Let's look at the following quadratic form. With this one, if we set w equal to 0, we get one of our GON-based ternary subforms. This one in particular represents every integer not of the form 9 to the k times 9l plus 6. Once again, we're only looking at when m is square free, so we can get rid of that 9 to the k part. And we can see that if instead of setting w equal to 0, we set z equal to 0, we get a regular ternary subform that we can use. So if we can show that this regular ternary subform represents every integer of the form 9l plus 6, then we're done. So since we're going to be looking under a p-adic norm, let's consider when our prime is not equal to 2, 3, or 5. And we can demonstrate why we chose those specific primes in a moment. But if we can show that our integer is represented under mod p, this will elevate to all p to the k. So what we do is we take our equation, expand it out, and once again, we're going to try to remove any cross terms by completing the square. And once we do this, we can now see why we chose our specific primes. We want to preserve as much information as possible from this equation, and so we need to make sure that we're not removing any terms. If we look under mod 2, then all of our 2's become 0s, and we end up dividing by 0, which is a problem. And if we look under mod 3 or mod 5, then this 15 halves w squared term will become a 0, and we'll lose that term. So because of our choice of primes, we know that 15 halves is going to be an element in z mod pz that is non-zero, which means that by the pigeonhole principle, there exists a y and a w that will give us our solutions, meaning that s of 0yw is going to be concurrent to m under mod p. Now, we just have to show it for our remaining primes. So if p equals 2, this gives us two cases, when m is even or odd, because since we're looking under mod 2, we're looking for when m is 0 mod 2 or 1 mod 2. So when m is even, what we can do is find the 2-adic norm of s of 0, 0, 1 minus m, and we see that this gives us something that is less than or equal to 1/2. Meanwhile, when we take the 2-adic norm of the gradient, evaluate it at the same point, and square it, we see that it is equal to 1. Since it is strictly less than, this means that all even integers are represented under mod 2. When it's odd, we can perform a similar process, this time specifically evaluating it at 0, 1, 0. We also get it's less than or equal to 1/2. Meanwhile, the square of the 2-adic norm of the gradient is still going to be equal to 1. So this means all integers are going to be represented under mod 2. Now, we still have the cases where p equals 3 and p equals 5, but it ends up being relatively similar, just with more cases, just time under mod 3 and mod 5. But it all works out to be the same. And so we know that all integers of the form 9l plus 6 are going to be represented by our regular ternary subform. This means that the larger form, by layering our regular subform and our GON subform, we know that this larger form is universal, and this proof is done. This got us along the line of thinking is that, well, we only had around 14 GON-based ternary subforms. Meanwhile, we had 913 regular subforms to work with. And so what if we could expand our search, and instead of looking for the GON-based subforms that were insufficient, just look for which quadratic forms possess a regular-based ternary subform that we can use. And we theorized that we could potentially use just these regular subforms to prove that the larger form is universal. And we're able to do just that. The following quadratic form possesses no ternary-based subform that we could take GON-based ternary subform we could take advantage of. However, if we plug in W equal to 0, we get one of our regular subforms. And using the Hensel's lemma and the technique we demonstrated with the previous proof, we've been able to show that this regular subform does not represents every integer that is not a multiple of 3. Now, it is important to note that this does represent some integers that are a multiple of 3, but what's more important is that we know that if our integer is not a multiple of 3, then it is 100% represented. So this gives us two cases. If it's not a multiple of 3, what we can do is just find an x, y, z such that it's represented by the ternary, meaning q of x, y, z 0 is going to be equal to m, and we're done. The much more interesting case is when it is a multiple of 3, meaning we don't know if it's represented by the ternary. Here we can break this into subcases, the first one being when m equals 3. This is relatively simple enough, it can be done by hand, and we see that q of 1, 1, 0, 0 is going to be equal to m. If it's greater than 3, what we can do is we can look at the number m minus 4. Now this seems like an arbitrary choice, however, when we take m minus 4, we see that it is 2 off a multiple of 3. Meaning that it is represented by our ternary. And since we've already covered the case where m equals 3, we know m minus 4 is going to be non-zero, or non-negative. And so there exists an a, b, and c, such that t of a, b, c equals m minus 4. So now if we take our larger form and plug in a, b, c, 1, we see that we get our ternary form plus 4, meaning m is represented by q. And therefore, since all non-negative square-free integers m are represented by this quadratic form q, it must be universal. So in conclusion, using our GON-based ternary subforms, we have been able to prove that 66 quadratic forms are universal. Once we began incorporating regularity into our argument, this allowed us to prove an additional 25 are universal, leading us with a total of 91 formal proofs that these quadratic forms are universal. Of these 91, for 50 of them, this is the first ever proof that these quadratic forms are universal. However, we are only looking at a list of 348 possible forms. We initially chose this list based on specific properties of these forms that we anticipated we were going to have to use throughout this technique. However, in all of these methods, we never ended up actually using these properties that this list was chosen for. And so theoretically, these techniques can apply to a list well beyond the original 348. And so it's possible in the future that these methods could provide further proofs than the ones we initially anticipated and provide much greater results. That is all I have for today, so thank you all for your time and attention. I'll gladly answer any questions you have. Yes, sir.
Can you help me understand actually where the geometry is? Why do you call this geometry of numbers?
Yes, sir. So the geometry comes in with looking at the actual subforms we've proven. And the subforms we were originally looking at, they were proven using a technique called Minkowski's convex body theorem, which originates from the geometry of numbers. And additionally, the invariant properties I mentioned that we chose our forms for, we chose them specifically so we could use those geometric properties. We never ended up actually needing them since we never got to actually not using forms without those previous results, but we highly anticipated it. Yes, ma'am.
It's a great job. So as you were exploring this concept, was there anything that surprised you or was unexpected?
I'd say the most unexpected thing was, for me at least, was using this regularity component. It was not something we initially outlined in our proposal for this project, and it was not something we anticipated using at all. After we finished our GON search, for a lot of these ones that were insufficient, we simply concluded that they were going to need some more powerful technique that we were going to have to develop. And then once we looked at this regularity component, we realized that this could be a lot more powerful than we initially anticipated, and it could be a lot more useful than what we initially proposed. And so we shifted our focus more on that, and so we could actually expand our results. So that was something that was a pleasant surprise for me. Yes, sir.
Hey, Andrew, do you have any applications for this kind of work, or is it kind of based in theory?
This work is highly theoretical in nature. However, like most number theory, it's very applicable in the field of cryptography. There already exists algorithms that can use quadratic forms in order to factor numbers and therefore can be used to execute cyber attacks. And so by having more universal quadratic forms in our tool belt, it expands on the work of that algorithm. Yes, Sam?
In your 91 proofs, did you ever find that proving one kind of automatically led you to prove a bunch of other ones, or were they all kind of independent?
They were all mostly independent. However, it's like if we could find one that possessed like we proved that, if I can go back, this subform represents L square free non-negative that are not of multiple of 3. And so then we could then look at our list and see, are there any others that possess this subform? For most of this did not, but I think there was 2 that shared a subform in common, so that was nice. But for most of them, it was a unique proof. Adrian?
What do you find to be the most challenging aspect of this project?
Trying to understand, if I can go back. This. I saw that notation and got very scared. I did not know what a p-adic norm was or anything like that, and so that was just a lot of literature review that had to get done beforehand to understand what I was actually trying to accomplish. Yes, ma'am?
I just have a practical question. Was all of this just on paper and you working it out, or was there some sort of, programming that you could use to help in solving some of the forms? Or was it all, analytical on paper?
So there was a bit of both. So we basically broke the project into 2 major components. One that had to be done almost entirely on paper, and the other one was done through code. And so our initial search for the subforms, that was all done by code. And then when I'm actually applying this, when I was looking when p equals 2, this all had to be done by hand because I'm looking at arbitrary variables. But when I'm looking when p equals 2 and I'm looking for these specific points, that I wrote up a code. I used Sage, which is a Python-based program. And I wrote up a code in order to find these specific points that would satisfy these conditions. And you would just need to plug in your equation, the prime you're looking at, and it would run through the possible solutions. Yes, Sam?
Could you go back a few slides?
Yes.
Yeah, right there. So on the right side of the equation, basically, is it you find the gradient, which is a vector, and you take the 2 norm, and then of that number, you take the p-adic norm? Because I see on the left side, that's a real number, but on the right side, it's a vector.
Yeah, so we take the gradient,
Yeah.
then we take the p-adic norm of that gradient, and so the p-adic norm is just going to be the maximum of the norm of each individual element of the vector, and then from there we'll square that. And so I kind of briefly ran through it, but with this one, we're looking at the 2-adic norm. 2-adic norm of 0 is 0, of 1 is 1, and 8 is 8. And so we take the maximum of that, which is going to be 1, and so that gives us our norm. Yes, sir?
So you were looking at universal forms. Are there any almost universal forms that represent all but one number?
I don't know of any off the top of my head that represent all but 1, but for a lot of them that we worked at, they represent all but a very specific class. And so that would be like our ternary forms. It would be every integer that is not of that form. And so it's you could usually classify the integers that were not represented because you're mostly looking at under modular arithmetic, so you have a lot of repeating groups.
Okay, let's thank our speaker one last time.
Excellent. No, that's Sam's. Thanks.
Good job.
Who's next? You're next, right?
Yeah.
Wonderful. Have fun.
Thanks. Talk about glue.
Glue?
Yeah.
Good talk. You ready?
Sure.
I got the crew. They're all here.
Found him.
I found them.
It's awesome. Thanks. I'm the only one, like, I guess the one nice thing. I'm the only one who knows.
You're the expert.
Like, you don't even know a lot of what I did.
Nope. I actually was like, I hope they record this so I can watch this later and later review.
You're like, I don't know.
I'm so proud of you.
Thanks.
It's a set.
There's literally no way.
Great job. That was so fun.
Still undecided on the med school? Okay, that's what I'll say.
Yeah. It's
situation to be in.
I know. It's come down to the wire, though. I have to decide on the 30th. And I go back and forth every day. I don't know. I might just have to flip a coin, honestly. We'll see.
Where are you down?
USIS up at Walter Reed, and then Eastern Virginia down in Norfolk, which would be nice, civilian school, but it'd also be nice to stay active duty and like hit the retirement.
Right,
You know, so, yeah.
Oh, there's not a bad choice. So.
No, and school's going to be the same either way. I think it's just going to be like quality of life. So
Yeah.
What's up?
Awesome. Finger gun.
Yeah.
I was struggling with that L. You know when you did this?
I was struggling with a lot of it. The scope of my math is Calc 3. I didn't take differential equations either.
Geometric. Oh, there's a lot.
Thanks. Enjoy class. I know. Yeah.
If you want to use this, you can.
Nah, I'm tall enough, I think. Otherwise, maybe I'll like leap across the screen. You know what I mean? Do some dancing in there too. Really keep it entertaining for the crowd.
That'd be good. Get your workout in.
You know, it's the last one in the morning. They're getting tired.
Oh, got a lot of chemistry people here.
I know. I'm excited.
Got some swim people here.
I know.
You're in the swim team. If you'd like any coffee, donuts, cookies, help yourself. We're around the corner.
Hi. Thanks.
Excited?
Yeah. It's fun. You know.
Are there any questions I should ask you?
I don't think so. I think my dad's gonna ask like an impossible question just because he can.
Okay.
I'm gonna be like, yeah, you sir, There, I'm gonna have to ask you to leave. Yeah, he texted me. He asked if it was okay. It was like really wholesome. I know. I know. Still got time.
Start on time. People are still coming.
Right.
Don't miss anything.
No. Ian, the whole chemistry department's here. Like, do any of them have class?
We don't need to go to class. Cancel class.
Who needs plebe chem, you know?
Chemistry faculty support them.
Yeah. Which is very nice to see.
I didn't have to send any emails because everybody else was sending emails.
Yeah, and you're like, I don't even have to. Right, right.
Your professor, your boss just-
Yeah. No way. You? What? I know. It's the swim team. What can I say? You know that, man. High energy group. Right.
from the 7th Company from Eden Prairie, Minnesota. Her service assignment is Medical Corps, and she's attending medical school in the fall, still to be determined where. And then she's a member of the Navy Women's Swimming and Diving Team.
Well, good morning all. Like Professor Schroeder said, I'm Midshipman First Class Chloe Skog. My advisors are Dr. Yates and Dr. So at the Naval Research Lab. And the title of my project is the formulation of barnacle-inspired underwater adhesives. So to better understand the challenge of adhesion in an underwater environment, first we need to understand just the common characteristics of glues. If we think about our commonplace glues, many start as a liquid glue and they transition to a solid, and this takes place simply by drying. If you think about Elmer's glue, super glue, they all just dry out on the surface they're on. But when we transition to an underwater environment where the Navy is every day, it's not as simple anymore. You can't just get rid of water where we are, and so we have to think about a new means of curing in order to come up with these underwater glues. So we can draw our inspiration from biology, and we can look at a few key organisms that do this very well. So mussels and sea stars use a unique protein modification process that's very complex, very time-consuming, and there's a couple of labs right now working on coming up with mussel-inspired adhesives. However, they're coming into challenges with synthesis problems, cost problems, and they're not really able to scale this up into something that would be usable. So our lab seeks to use barnacles as our inspiration, where they use a unique protein aggregation method, which is much more simpler of an approach than mussels and sea stars. So barnacles use protein aggregation, and that's simply the association of proteins into larger structures that tend to be insoluble. So a barnacle secretes a liquid protein solution, it polymerizes over time, and it turns into a very insoluble, fibrillar, sticky network, and that's all some things that we want to emulate in our own glues. So in the same way the barnacle utilizes protein aggregation in their cements, we want to use commercial proteins. We're using 3 whey derivatives and 1 chicken egg white protein. We want to manipulate them to form aggregates to create our own underwater adhesives. And this manipulation comes in the form of what we call an initiator, which is basically chemical soup made up of a denaturant, a reducing agent, and an aggregating agent. So we've been able to successfully do this with a protein called bovine serum albumin. 2 summers ago, me and 2 of my lab partners spent the summer optimizing this formula for bond strength. And it was a novel 2-part system where, again, we had that protein solution where it was just whey protein derivative dissolved in water, our initiator, which was, again, the denaturant, the reducing agent, and the aggregating agent. And it was able to form this relatively elastic glue that was set and cured all underwater. And this work was published this year, which was really exciting. Last year, as a part of my capstone work, I did this process again with a new protein called alpha-lactalbumin. Me and my lab partner, Jackson Fuller, were able to design a new unique glue that was deployable via syringe, which was really exciting for us and something we hadn't been able to do before. Again, this was scalable, easily deployable, and cost-effective like our BSA system was. So to understand a little bit more about the chemistry of what's going on in this glue, first we start off with a protein, and it's in its native folded state. We have to add our denaturant, which partially unfolds our protein and allows us to start working with it a little bit more. However, you can see those pink lines, those represent disulfide bonds. There's still some bonds remaining that we need to reduce, which is why we add a reducing agent. Now we have a completely unfolded protein that we can remanipulate to induce that aggregation we want. So by adding an aggregating agent, we can induce protein aggregation and remanipulate it to have a highly structured, highly ordered beta sheet conformation and ultimately form insoluble aggregates. So you may be asking yourself, you spent a year ago working on this, you've already come up with 2 glues, and you seem to understand a lot of the chemistry about what's happening. What are you even going to do in your Trident project? So while we're doing this all in the underwater, seawater environment, we want to think about the salts that we're working with in seawater. Salts themselves act as denaturants, so we want to better understand how salts are impacting that denaturation process. Are they stabilizing our protein? Are they destabilizing it? Are they relatively speeding up or slowing down relative chemical denaturation? And are they changing the temperature at which our glues gel? So this all boils down to the main goal of my project. How can we manipulate denaturation to better understand underwater curing. So first I wanted to create an objective scale of denaturation to really pinpoint how effective salts and other extremes are at denaturing, that first step, again, that unfolding of the protein. We can characterize these compounds into two places, either chaotropes, where they're inducing a lot of disorder into the system and they're breaking those structures we have, or they can be characterized as a cosmotrope, where they're inducing order and stabilizing the native state of a protein. So I sought to do this by adding salts. I used the four major components of seawater: sodium chloride, potassium chloride, calcium chloride, and magnesium chloride. And I wanted to see if I could create a physical scale of how effective they were at actually denaturing our two proteins of interest. To do this, I compared it to our urea system, which is what we had used in the past, that work that I did 2 years ago. And we saw that to do this, we used differential scanning calorimetry, and we found the minimum heat flow required to melt our proteins. Then we were able to compare it to our standards when we did it with salt in our protein, and we saw that for BSA, that first protein system, we saw that all salts were acting relatively chaotropically. So they were speeding up that denaturation process and inducing more disorder into our system. When we did this for our second protein system, alpha-lactalbumin, we saw almost the exact opposite, which was pretty surprising at first. We saw that for all four of our salts, including urea, which was our initial standard, they were all acting cosmotropically. So they were inducing structure into the system, and they were stabilizing that native state of the protein. Upon further investigation, this made a lot of sense because alpha-lactalbumin has a calcium binding site in its protein structure. So by adding calcium specifically, but other ions that are similar in charge, size, shape, valency, they all sought to further induce more order into our system. I also wanted to look at other denaturants we commonly use in the biology and chemistry labs. I wanted to see if we could maybe find something that was more effective, that would be more cost effective, potentially less toxic. And so I did this by looking at these four were characterized as relatively chaotropic from previous work done in other labs, and the bottom four were relatively cosmotropic in previous work. And I wanted to see if that still stood true for our two protein systems. We saw for BSA that most acted chaotropically, and we saw that for ALA, most acted cosmotropically. This kind of correlated to what we saw before, but it was still pretty interesting that, especially Trident X and vanillin, which were two really, really strong chaotropes on sugar systems instead of protein systems, were good, but they were not great at denaturing our proteins. So what was really the most exciting thing that I saw was that when we put the salts that I had tested originally back on the same graph, we saw calcium chloride was acting actually more effective than those extremes that we once thought would be most effective for our system. For BSA, calcium chloride was the strongest denaturant, and for the ALA system, it was actually the worst. So I wanted to see, wow, salts are a lot cheaper, a lot less toxic, and they're already in the environment we're working in the seawater environment. Can we utilize this by adding salts directly to our glue formula to better enhance some of those adhesive and material properties we're trying to find in our glues? So in general, the denaturants were more effective in reducing melting temperature for BSA than they were for ALA, but ultimately the salts were the most effective denaturants we wanted to continue investigating. So to do this, I transitioned into a relatively qualitative test of gelation testing, where I simply add the protein dissolved in water and the denaturant. So I started by adding salts, and for our first system, BSA, we saw that there was actually no successful gels. This is generally indicative. If we can create a solid through this process, generally we can create a glue from when we add the other components of our formula. But if it doesn't gel, it's generally indicative that this is not something we want to continue pursuing. For the ALA system, we did throw in some of the more unique cases of our extreme denaturants I tested previously, and I was able to get some successful gel tests. For our third wave derivative, beta-lactoglobulin, we saw that there were no successful gel tests in any of the cases we investigated. And finally, for that chicken egg white protein, lysozyme, we saw this was the only case where we had successful gelation testing with just salts and protein. This was really interesting, and this helped guide my future work. I was able to look at BSA and ALA, and although they didn't have successful gel tests with our salt cases, we already had the precedent that there were two successful adhesive programs, So I transitioned my approach to adding salts as a secondary denaturant in addition to what we already had in our formula, which was urea, and I wanted to see how that would impact those material and adhesive properties. For the BLG and the lysozyme systems, we decided not to continue to pursue these avenues because for BLG we had no successful tests, and for lysozyme, while we did have some interesting cases, it's an extremely expensive protein and it was very challenging to scale up. So it wasn't something, given our two already successful programs, that we wanted to continue to pursue. Next, I transitioned to more technical testing. I used a rheometer, which allowed us to characterize some of the viscoelastic properties of our glues. The first test I did was a curing time test, where I was able to pinpoint the exact time it took for our glues to transition from a liquid to a solid. So this crossover time is when, if you think about super glue getting on your hands, it turns into a solid almost instantly. You have to pick it off. That's the kind of time point I was looking for in these tests. As I added salts directly to that glue formula, I was able to see a wide range of results. By adding sodium chloride, I had a significantly slower curing glue than by adding my two divalent salts, calcium chloride and magnesium chloride. This was really, really exciting for me as we were able to expand the working window of our glues. If we thought about the potential naval applications for this, there's some settings where we would want a glue to cure within a few minutes. And with calcium chloride, we saw in our most extreme cases, it could cure within almost a minute and a half. But also on the flip side, if we think about sodium chloride, we have about a 6-minute working window where we can apply this glue to very large areas, and we can be a lot more methodical in our approach. This was all things we were really excited about. The second rheological test I looked at was amplitude testing. This took cured glues, and I placed them under strain to understand the stiffness or the hardness of the glues. So storage modulus can be equated to stiffness in a sense. By investigating the different salts, I saw that, again, sodium chloride was the most stiff glue that we saw, and calcium chloride was the least stiff glue that we saw for that first BSA system. Beyond salt identity, I also wanted to see how concentration could have played a role in the modulus of our glues. And I want to point out the difference between the blue bars and the yellow bars. For all of our cases here for BSA, we saw that as we increased the concentration of salt, we were decreasing the modulus of our glues. And for all cases but sodium chloride, this was a statistically significant change. So just to help visualize this and the elasticity portion, as you can see when you're picking up the glue, it begins to sag a little bit. The BSA glue is very stretchy, moldable, bendable glue for all of our applications. So again, just to reiterate, salt, both identity and concentration of our salts impacted the modulus or the stiffness for our BSA adhesives. I did the same approach, but with our second protein system, alpha-lactalbumin, and again, I saw a very similar trend. The notable outlier here, though, is calcium chloride. It's a much higher bar than what we saw for BSA. Again, this makes sense if we think about what I talked about previously. Alpha-lactalbumin has that calcium binding site. So by adding calcium directly to our glue, we're kind of stiffening and adding more structure into our glues, which is likely why it's much more stiff than the other ALA adhesives we saw. Again, when we investigated concentration, we saw a similar trend for our two monovalent salts, that as we increased concentration, we decreased the stiffness of the glue. But interestingly, for the divalent salts, calcium chloride and magnesium chloride, we saw no noticeable differences as we increased the concentration. This glue was a lot more hard and brittle when compared to BSA. If you tried to bend it or rip it, it would pretty much just snap in half. So again, increasing concentration decreased our modulus for ALA, but this was only for our monovalent formulations. Moving past our material properties of our glues, the big most important thing is the adhesive properties. How strong are our glues? How effective are they at actually bearing force? So to do this, I used a lap shear method, and I tested on multiple different materials, mostly metals, plastics, and rubber, as they're all ideal for underwater repair for the Navy. And then I also tested in different lab environments, distilled water, artificial seawater, and individual salt solutions. I used a 3D printed mold for my lap shear samples to ensure the same overlap and glue width and thickness. And then I also cured all of these samples underwater for 1 week before testing. For our lap shear testing for BSA, we saw that sodium chloride had the lowest bond strength of all the glues we looked at. We also, in previous work, had added silica as a material additive to enhance and boost some of the material properties. And in previous work, we had seen that by adding silica, we could increase the bond strength. So I wanted to do the same idea for this and see if salt and silica had any different trends than we saw for just silica and the glues. Interestingly, for BSA, we saw that upon adding silica to our salt formulations, we saw that all 4 cases decreased. And this was a significant decrease for both calcium chloride and magnesium chloride. Interestingly, this was the first failure we had seen too with our glue. For magnesium chloride with silica, it actually didn't adhere to any of the surfaces we tested. When I did this again for alpha-lactalbumin, I saw that potassium chloride had the highest bond strength for these cases. And when I added silica, it actually increased the bond strength for all of the salts we tested. This was significant for sodium chloride and magnesium chloride. And what was really exciting about this was although the ALA system is a little less developed, we saw no true bonding failures, which was really, really promising. So we saw that both material additives in both the BSA and the ALA formulations are going to have varied effects. And this is, again, really exciting. If you think about different applications for different glues, you wouldn't want the strength of superglue adhesive to be on a Post-it note. The point of a Post-it note is to be easily removable, and the adhesive is actually pretty weak. And same thing for superglue. If you're trying to actually superglue something, you need something that has really, really high bond strength. So the fact that we can add something as simple as salt to our formulations and push the extremes on both the high and low side of bond strength is something really exciting and really promising for naval application. I wanted to move a little bit beyond laboratory settings and to see how these glues really worked over time and in different environments. So I expanded my test beyond 1 week, which was the original case we looked at when considering all of our salts, and I expanded it to a 4-week mark, an 8-week mark, and a 12-week mark. What was really exciting about this for the BSA formulations, we saw that all of our long-term testing cases were actually higher in bond strength than any of our original testing. This shows that as this glue could be out on a naval vessel, it's actually going to harden and strengthen over time while it's out on those vessels. For ALA, we saw pretty similar results, that our highest case was at 4 weeks, and it was almost double the bond strength of our simple distilled water case. And while it tapered off a little bit over time, it was still really promising that our bond strengths were relatively comparable even after almost a 3-month span. And the only reason we stopped at 12 weeks was just due to time constraints, but hopefully we can continue this work over the summer and into next year and see really if we can map the longevity of these glues and see how long they can continue to bear force. Another testing I did was wanting to look at the environmental cases. I wanted to see if I could push beyond the lab settings. You know, we're using artificial seawater, which is a relatively contained environment, but could I apply this to the real settings that the Navy is going to operate in? So I obtained some brackish water from the Severn River, which is 53% salinity of the ocean, and then I obtained some Atlantic Ocean water from Virginia Beach, and I did the same lap shear process. For this, again, we saw some pretty interesting and surprising results. For our BSA formulation, we saw that both of our environmental cases were almost 3 times as strong as our original lab settings. This is really, really, really exciting work. And I know I said really like 4 times, but that's because it is. Because we're seeing that as we're transitioning these glues into real environments that we can operate in, the glues are actually only getting better. For ALA, we saw a less noticeable, less exciting thing. However, again, this glue is still in development, but we're still not seeing any failures, which is something I really want to point out, that even when we transition these glues into the environments that the Navy would be operating in, we're still having successful adhesives. So again, these 2 tests, the long-term testing and the environmental testing, showed a proof of concept that we were able to expand this underwater adhesive theory beyond just lab settings, and we were able to push both time constraints and environmental conditions. So what did we learn from all of this, right? We were able to develop a successful underwater adhesive system with 2 separate proteins. And our new alpha-lactalbumin underwater adhesive was completely developed, optimized, and deployable here at the Naval Academy. Some technical takeaways from a scientific perspective: we were able to expand the working window of our glues to have a working range of anywhere between a minute and upwards of 6 minutes for our glues before they set. We were able to push the bond strength on both extremes again by adding just material additives and salts to our glues, and we were able to expand the environmental conditions and time window beyond our laboratory setting. Why does the Navy care? That's the big question. There's a lot of potential applications for these glues in the Navy. Lots of communities have highlighted their interest and their need for an underwater adhesive, and we see that there's special cases in the special warfare community where ordnance disposal could use a glue like this. This could turn into an underwater welding alternative for the CB community, and waterline and hull damage repair for naval vessels is a really big thing that I want to draw your attention to. So this is something that me and my lab partner were able to investigate further. We were invited to the Naval Research Lab to help complete 2 science and technology demonstrations for the Office of Naval Research. Again, this was at the Naval Research Lab, and we were able to show that we could deploy our BSA adhesive at scale with a 3D printed bayonet applicator. Again, this is over a square foot. So this is really exciting. Our lap shear samples were just about the size of your thumb, about 1/2 inch by 1/2 inch of glue, but we were able to apply this glue over a whole square foot on a vertical surface to simulate, and we saw that even after curing for just 20 minutes underwater, we were able to hold 185 pounds. And we were only limited because we ran out of weights to put on top of it. So there's a great potential that it could have potentially held even more weight. And then again, I just want to emphasize we were able to do this with real live operators. Me and my lab partner, Jackson Fuller, we were not trained at all to do this. We just got in the tank, sat on the bottom, and tried to figure it out. And we were able to show that, you know, in handing these glues and these tools over to Navy divers, they could really implement this into the fleet relatively easily. So with that, I just want to thank everyone for their time, and I'd like to open it up for questions. Captain Goodale.
Captain Goodale, the women's swing dive team over at Hey, Chloe, congrats, this is awesome. But, and also I think perhaps touching upon your future profession as a medical professional, I'm just kind of curious. So it looks like some of these adhesives create like a gel-like quality, and thinking about the future of warfare, particularly in the Marine Corps, like we're going to be operating a lot of littorals, and perhaps injuries are going to be like kind of flesh wound injuries are going to be sustained on individuals in under or around the water environment. Do you think there's any kind of medical application for like an adhesive gel, like Band-Aid, that could be used in a pinch in order to continue operations?
Absolutely. What's really exciting about this is the most like toxic element we have is a surfactant, which is just a type of soap. So again, that's kind of the goals of by adding salt, right? Salt isn't, I mean, you use table salt, you eat it, you use it all the time. It's a really quick approach, and it's really non-toxic. So while we haven't investigated biomedical applications, there's definitely an avenue where these glues could work there.
Awesome, thank you. Good job.
Oh, thank you, Lou. This is great. So the question I have for you, I'm intrigued by the workability of it when you're manufacturing it before you go to deploy it. Does it cure an air at all, or does it not cure it until it's in water? I mean, how much time do you have to work with it before you load it into the syringe?
Yeah, so for our BSA adhesive, it does cure in air. We have to put it into a 2-barrel cartridge so that they don't mix, but then once they get into the tip of the applicator, they start to mix. And that's where we have that roughly 5-minute window. What's very interesting for alpha-lactalbumin, which is that second glue we developed here, it's deployable via a syringe in just one tube, so we can mix the 2 components. It doesn't cure in air at all, which is really cool. We've been able to leave it like in the fridge for upwards of a couple hours mixed before we come back to it and apply it underwater. And it only starts that transformation from a liquid to a solid once it's actually in seawater.
Chloe, I'm an adjunct here, but in my real job, I built composite naval vessels. And so the toxicity of the epoxy resins that we use is something that's really difficult to work with and get approvals for. You mentioned you use whey protein.
Correct.
You know, that's a huge byproduct of waste product of making Greek yogurt. We can't get rid of it. So could we apply whey protein as a byproduct that's ecologically friendly as an epoxy resin for infusion into carbon fiber?
Yeah, potentially. Some interesting work I did last year, we actually just bought a tub of protein powder from Amazon, and we wanted to see, if we transitioned away from like lab grade materials and truly pure proteins, if these mixes along with, other additives in them, if we could still make a glue. And it wasn't as effective, but we were still able to create a glue with the commercial whey protein we got. And it held a significant amount of force, which was pretty exciting, pretty comparable to our BSA adhesive. Professor Harrison?
Great talk. So you've modeled this after the barnacle, which has a protein that is working in the adhesive. And you have differences in your BSA and your other protein. So and I know NRL has characterized the sequence of that protein. Have you thought about looking at the actual structures of all three of those to try to tease out why the differences in behavior with different salts and so on?
Absolutely. So it's interesting you point that out. Obviously, 4 proteins are going to have very different structures. We see for BSA, it's mostly alpha helices, and for alpha-lactalbumin, it's a lot lighter in molecular weight, and it has some alpha helices, more random coil. I think the most interesting thing that I saw was that beta-lactoglobulin we tested had mostly beta sheet characteristics, which is likely why it wasn't as successful. Something I was potentially thinking about, we have to change the initial, protein into something different, and it has to be insoluble over time. I think it's potentially could have been that since both the BSA and ALA had a lot of alpha helix character, and once we induced aggregation, we created beta sheets. When we start with beta sheets that are already soluble in water, we can't make an insoluble aggregate that's also forming beta sheets, if that makes sense. So I think that's why we had some of those challenges. And we didn't investigate lysozyme as closely just because of those cost elements, but since it has relatively similar secondary characteristics, it's likely that we could have made a glue out of it as well.
I would like to commend you on a great presentation and everything. I followed you from the proposal and everything. And I want to actually share with the community here present, because now the auditorium is packed, how important it is to actually be able to fully understand the depth of your project, how important it is to actually spend time on understanding these issues. I mean, you had a head start, I believe, as a sophomore or something, and this is where it leads after 2 years of working on it. And to actually emphasize how important it is for the scientific community to do these parametric studies. They are tedious, they are meticulous, they are extraordinary. And like if you produce one slide in which you can say, I'm happy about it, you kind of are like at the pinnacle of your research, because that may not be the case in all that you've done. But to actually make a statement about the depth, the true research understanding of what does it take to actually convert something that is a magnificent idea and like something exciting and something that you try as a toy problem, and actually lead to full understanding of the depth of what has to be known in order to truly use it for applications. And I really appreciate your effort and persistence in staying on the same problem for 2.5 years or so. And for my future, our future Tridents, that is the way to go.
Thank you, ma'am. Professor Lynn?
I was very curious about, if you had two questions, if you had an idea when you looked at the plot of bond strength over time, and you were seeing that it really did last for a long time, which was very exciting, but it did increase and then decrease. Do you have a sort of molecular level explanation for that?
In terms of the alpha-lactalbumin, I will say it was probably my fault. I didn't do a great job. What's interesting with alpha-lactalbumin is it starts to form bubbles underwater. So when you deploy it by a syringe, there's some bubbles that are left in the syringe. When you put it underwater, you try and trap the water in between the two substrates and then also the glue. While we do put a 250 gram weight on the top of it, I do always find that there are bubbles left. Once we actually break the samples, you can see that we can kind of look at the failure pattern to better understand what's going on. And for our ALA samples, we tended to see in that 4 and 8, or the 8 and 12 weeks, we saw like a lot of holes, but then that matched the same hole on the other side. So that was indicative that a bubble was forming rather than just adhesive or cohesive failure. So I should do it again. I'm going to make Dr. Yates do it again over the summer.
And my second question was about, in a realistic Navy environment, often some of these applications will involve cycling between wet and dry, right, going back and forth. Have you looked at any experiments that involve cycling to see what the effectiveness is on the
We haven't done a ton. Generally what we do is once we cure in water, it's in water for a week, and then immediately we pull it out and put it on the tensile tester. But a couple, I guess last summer we looked at some testing between curing in air and then putting it underwater, or curing it underwater, or like deploying it underwater and curing it underwater. That would be some interesting testing to do in the future, of deploying it underwater, curing it underwater, maybe leaving it out of air for a couple days and then seeing. But I mean, if we're able to do that, then we're really mimicking the barnacle, which would be cool.
What's the cost like between BSA and ALA? Are they comparable, one expensive?
No, both of them are relatively cheap. I don't know the exact parameters, but I think we can get about a kilogram of BSA for, I think, a couple $100. And again, that's laboratory grade. So if we knock this down to something that the Navy would be using, where we don't need as pure of chemicals, it is still a really cost-effective approach.